Mr. Paul Lang, it's the Senior Director, Conformity Assessment, Product and Personnel Certification from ASME, which we say here ASME. So, Paul, please welcome, and you can say a few words, please. Meanwhile, let me say one thing. You have a button in the bottom of the screen down on your right, where you can change the language. You can change for Portuguese, which is the translation, for English. And you can, if you don't want to listen, the person is speaking in English behind you with the translation, you can set this as well. So this is small button, it's a globe that is down in your screen, in the middle, in the right side, you can set this. Please, Paul.
Okay. Okay, thank you very much. Thank you, Pedro and Antonio. It's a real pleasure that we finally have the opportunity to put one of these events on. Like Pedro said, this is the first one we're doing, probably of a few, for a collaboration with Abendi on codes and standards, specifically ASME codes and standards, their use in Brazil. ASME and Abendi's collaboration goes back a few years, but it's been very close over the last couple of years, where Antonio and ASME, Chris Mahler, have been working on educating and bringing to life the standards that are already popular in Brazil, but giving better access for the individuals in how ASME standards are developed and how they're used around the world. We initially had, I think, Antonio can correct me if I'm wrong, we had 3 events that were face-to-face in 2020 we had scheduled. And we were really looking forward to these type of activities with the workforce in Brazil. But the COVID had to kind of put a damper on those type of activities. So Antonio and Chris, and again, I'll thank them all through the workshop here. They quickly switched around and found ways that we're able to meet online and be able to give some type of connection and training to individuals who want to know more about the ASME standards and how they're utilized and how they're developed. And in doing that, they brought some really good subject matter experts to the table here for the group over these next 2 days. They're not only premier people in their field, but they also sit in very important positions in code committees that actually develop the standards that you utilize in your industry, specifically in the oil and gas pipeline industry. So I look forward to today. Like Pedro, I don't want to sit here and talk a lot. I like to get right into the information because I know that you'll find it intriguing and interesting and you'll have questions. So I want to say thank you to everyone. I believe there will be more of these to come. If I know Antonio and Abendi, they believe this is a very good benefit for the workforce in Brazil, and ASME is right along with them that would help them to develop these type of activities. So thank you again for joining, Antonio and Chris. A great job in putting this together, and I look forward. I'm interested in hearing the topics and working through them. And Pedro, appreciate Abendi's work with ASME. I think it's a great partnership and collaboration, and we look forward to many events in the future between our 2 organizations. So thank you all. And Antonio, I'll turn it back over to you. I appreciate it.
Thank you, Paul. So let's start our session. Please allow me to introduce Chip Eskridge, which will be our first presenter. He is chair B31.1 and works for Worley. Mr. Eskridge is the current chair of B31.3 Process Pipe Section Committee and an active member since 2001. He is also a member of B31.5 Refrigeration Pipe Section Committee and B31 Materials Technical Committee. Mr. Equity has 40 years experience in the petrochemical and power industries, covering several different areas of power industry. Holding responsible positions include those in process engineering and design, project construction management, plant commissioning, and operations. Mr. Exredy is governor appointed to Kentucky State Boiler and Pressure Vessel Code Committee. So, Chip, welcome. I pass the word for you. Thank you very much.
Okay, well, thank you. I am trying to get my screen here going. Let's see here.
Meanwhile, let me use this time and say that after the presentation, at the end of this morning, we will have half an hour for questions. You can write you send the questions for us, and we are going to read the questions, and of course, Chip will answer. So feel free to write your questions. And we have time to discuss each one.
Okay. Can you see my screen?
Yes.
Okay, and should be in, let me see here. Go to presentation mode. Let me stop sharing. Let's see.
Yeah, we can see your screen.
Is it full screen?
Chip, it is it's the presenter screen that you have on right now.
Okay, okay. Let me get to the other screen here. See what this does.
Chip, do you need the camera on you?
No, I that was on my laptop, so I'm trying to go for my. See here. Got too many screens here, and I don't see my option here. Let's see here. Let me try to do it. Try to do it here without the. You still see my presenter's view, right?
Yeah, we see the ASME policy and the first one, Abendi workshop.
Try it again.
Yep. Chip, put up your presentation and then okay, you might want to go to display settings, or
yeah, that's where I was, and it's
yeah, then go to the bottom. Yeah, open that. Okay, hit duplicate.
There we go. How's that?
Yeah,
Connor.
that's it.
There is a reason why I'm here, except for just to look good. So please be ready.
Yeah.
Thank you, Chris.
Okay. Well, good morning. I'm Chip Askrich. I'm the chairman of ASME B31.3, or as many refer to as ASME B31.3. So I've got, I'm the current, let's see here. I've got stuff going on here. There we go. I'm the current chairman of ASME B31.3. I am not an employee of ASME. So the presentation that you're about to see is expressed opinion of myself and my 20 years being on the committee. It's again, I'm not a ASME employee like Mr. Lang and Chris. So so if you do have and we'll get into this and questions about the presentation, once again, it's my viewpoint for my 20 years being on a committee as the officer. All right. So again, I am Chip Askrich. I'm the current chairman of ASME B31.3. I've started this term as chair in 2020. I was the past vice chair from 2017 to 2020, and for 8 years I was the chairman of chapters 5 and 6 of ASME B31.3, which is the fabrication, examination, testing chapters of the book. I am a 570, 510 certified inspector. And for 8 years, I did sit on a government jurisdictional board here in the United States, representing the welding metallurgist. I am a professional engineer, which my license is in mechanical engineering, and I also licensed in metallurgical engineering materials. So let's get started. For for the next couple of hours, we'll talk about ASME B31.3. But there are 7 other construction code books that I'd like to just give a quick overview. B31.3 is the process piping code book, and it's written around a 20-year service life for the piping. Besides, refineries, which tends to be a very stable, mature business, you still have different crudes coming through, and over 20 years, material changes happen. So again, think about B31.3 as a 20-year construction code. I mean, it can last longer than that, but the rules are focused for the piping system to last 20 years. As the afternoon, you're going to hear a presentation on 31.1, which is power piping. Power piping is a little bit more of a robust piping code book, and it has an intended service of 30 years. And another popular used book in the ASME collection of piping is B31.8, which is gas transmission, and that's written around a 50-year service life. A couple other construction code books that I want to mention is there's one for liquids. A lot of gasoline and is actually pumped, and crude is pumped here in the United States underground, not just natural gas. So we have a code book 31.4, 31.11. It's similar to B31.8 because it is a buried pipe, but it is different. And we won't get into that today, but just let you know it's there. B31.5 is a refrigeration piping book. It deals with a large-scale refrigeration system. It's often referred to as a B31.3 light. For instance, it doesn't have a lot of radiography rules in there. Only if you have a highly flammable refrigerant do you do any radiography. So it follows a lot of the concepts of 31.3, but not as imposing. The last 2 construction code books I want to discuss is 31.9 and 31.12. So 31.9 is the building services piping code book, It's in this country, it's actually legislated by law in a lot of the big buildings where you'd have some heating steam, maybe circulating hot water for heating. It's a really low pressure utility code. Steam pressure cannot get over 1 megapascal, and you'll find no radiography in that. A lot of threaded pipe. So it's got its position, but not inside typically a refinery or chemical plant. More like a commercial building, a very large commercial building. And lastly, the last construction code book I want to mention is 3112. It's been around for 20 years. There's a vision in the future that in order to have reliable power at a local level, that fuel cell technology will develop and be fueled by natural gas or possibly hydrogen. And hydrogen is a very small molecule, hard to contain. So ASME came out 20 years ago, developed B3112, and it's for hydrogen handling, typically at a residential, industrial level, and there's a pipeline part to it also. All right, back to 31.3. 31.3, the intended service for 31.3, the ASME process piping code, is first and foremost is the petroleum refinery industry, both onshore and offshore. Actually, that was the title of 31.3 back in 1959 when it was first published. They had a placeholder for the chemical manufacturing piping, which was B31.6. But B31.6 never got issued. They found so much similarity between what the refinery industry needed and what the chemical industry needed that they drafted the book, never issued it, and just merged the rules into 31.3. And the title of 31.3 eventually became the Petroleum and Chemical Piping Code. 20 years ago, we shortened it to call it just the Process Piping Code. So the first two are what the original intent service for 31.3. Since then, the natural gas industry uses it. The ore, metals and mining, ore processing industry uses it. A lot of sulfuric acid, different acids they use in that industry. So they find 31.3 the right fit. Also pulp and paper. They use a lot of caustics and acids in that industry. So they use 31.3. The semiconductor industry has a need to manufacture high purity solvents for the making of microelectronic chips. And with that, they find 31.3 is a good kind of upstream code when you actually, because of the rules that allows us to, let me see, let me do the rules that are able to contain those solvents. And then lastly, the cryogenic industry. So when you get down to very, very cold temperatures, minus 269 or 425 F, where you're using liquid helium, 31.3 is used often. NASA uses 31.3. In fact, we have a study with NASA that we help co-fund because of the cold temperatures of space. And again, at NASA, the astronauts fly on 31.3. All right. So what 31.3 is not intended to cover is a piping system that's covered by another ASME code. So for example, there you should not issue a piping system and say we want this to meet ASME B31.1 and B31.3. You should pick one or the other, not both of them. It's not intended to handle that way. Each code book has its own rules for its intended service. So don't, if you are a designer calling in, don't specify 2 code books for the same application. Plumbing, it's not intended to be used for plumbing. The International Plumbing Code is out there for that. It's not also intended to be used for fire protection. The International Fire Protection Code is out there for that. In the pharmaceutical, the making of medicine, ASME has the bioprocessing equipment standard, which deals with a lot of polished welds, a lot of polished surface. Not so much strength they're focused on as much as quality, the weld quality. So that's another one that ASME B31.3 is not intended to cover. Then you have your drinking water, your potable water. That in this country, we have a different standard, which is the American Water Works Association that covers that. Pressure vessels, it's including internal piping, as ASME B31.3 is not written around that, although I can tell you, I have in the past on pressure vessels specified internal coils to meet ASME B31.3. The code does not prohibit that. For some reason this is timing, my slides are timing out. So apologize there. And then also piping around rotating equipment. That piping on the skid is the owner stays with the skid, and the owner can make it to ASME B31.3 or can choose not to. We don't impose those rules on a rotating piece of equipment. And then post-construction, once the piping system is built, hydro tested, handed over to the owner. Now the post-construction standards take over for ASME, and there's some API standards that would apply for in-service maintaining of the piping. I want to mention that we do have a international participation on ASME B31.3. This group, this is the what's in the 2018 book, but I can tell you in the last 2 years, we've nearly doubled this size of group. I see individuals in here from Australia, from the UK, from Norway, from France, from Malaysia, so from the Middle East. So we'll get into this, but we encourage participation from around the world. And then ASME B31.3, we have an international review group that here's something more about it. We have 3 technical meetings a year. The International Review Group will meet in January, April, and September. And then to help facilitate these international members that don't have a chance to come to the U.S. and learn through our face-to-face meetings, we will have 3 workshops per year in February, June, and October, just to help the international working group understand how to change the code, how to not so much, again, you would be a committee member helping to improve the code, but with that, the benefit is you'd get more knowledgeable on the code. The chairman's Matt DeLong. He's the international chairman, and there's his email if you'd like to reach out to him and express interest in participating as an international member. Also at ASME, all the standards and codes, there's a way to get an interpretation request from ASME. In the 31.3, back in Appendix Z, we have a sheet that says you can reach out to Mr. Riyad Mohammed, his email there, or there's a website there to enter a question on a particular chapter or a particular paragraph, particular requirement. That's in all ASME books. It is in 31.3. The one thing about interpretations, though, is the question cannot be consulting. In other words, your question can't be, well, how much corrosion allowance should I use? Or your question cannot be something along that line where you're wanting to better understand the code. Your questions are written so that ASME can provide a yes or no response. And I've provided an example of that. For instance, this might be one question that we would receive. It would come in for normal fluid service, does ASME B31.3 permit omitting the leak test with the owner's approval? And we would respond, I feel like the committee would respond, no. So again, write your question in a yes or no response. And typically we ask you to, usually there's a paragraph in particular that you have a question with. So cite that paragraph if you can. This is just a typical question. And that answer, by the way, as I said earlier, this is not necessarily the express written position of ASME. This is a question that I came with. This is how I feel the committee would respond. But if you do right here, do send into the Riyadh, you will get a official formal interpretation answered from the ASME committee. We meet twice a year, so the interpretation could be a few months in coming. All right, let me get through that. Sorry about that. So here's our agenda for the day. Part one, I'm going to go over some general requirements. I'm going to continue after a break, finishing up the general requirements. I'm going to give an example problem at the break for you all to look at. We'll come back and I'll work it, show you the answer. Each one of those are about 40 slides, the first two, and then we'll conclude with maybe another 30 slides, combine the working with best practices and code changes, and then we'll end with the Q&A, and we'll be done for this morning. So let's get on with general requirements, part one. So in this section, I am going to go over the B31.3 structure, the roles and responsibilities of different individuals using the code, the educational and experience requirements for the designers. Later, we'll talk about the same educational and experience requirements for the owners and inspectors. But right now here in part one, I'm going to be focusing on the design portion of the code. The numbers behind the why you do pick a Schedule 40 pipe, some of the numbers that as an inspector you might be calculating. With that, we're going to get into a little bit of stress theory, looking at a cylinder, which is how pipe is designed as a cylinder, and we'll go through a straight wall pipe sizing. I'll show you a calculation. We'll talk about branch connections, reinforcing the openings. Sometimes you stab in a branch into the header. Sometimes you use repads. Sometimes you might use a coupling, like a threaded coupling or a socket coupling. And often you might see OLETs. When do you use each one of those? I'll talk about what we refer to it in the committee as listed and unlisted materials. Also listed and unlisted components. These are the listed components. Listed materials are things that are pre-approved to use. And the unlisted materials and the unlisted components are items that aren't in the code, but we provide rules on how you can use something that's not in the code and still meet B31.3. All right, so here is the structure of the actual ASME book. We have 10 chapters. You can read them down through there. I've put out to the right, like the first one is subgroup A. Within our committee when we meet, and also if you would ever become an international participant, we have 8 committees. Each one is assigned a certain portion of the book to maintain, to improve, to actually when interpretations come in, if the question happens to be around a fabrication question, we would send it to subgroup E for the fabrication group to write up an interpretation. So in this workshop, I'm only going to be able to cover the first 6 chapters: scope, design, materials, standard components. We'll get into fabrication, assembly, and erection toward the end, and finally inspection, examination, and testing. I found that's a good place to end it today. If we continue in the future with another workshop, I'll be able to talk about the last 4 chapters, which is your non-metallics like FRP pipe, lined pipe is in there. Your category M rules, which is for highly toxic materials. High pressure, when you get up above 2,500 pounds, which is maybe 100 megapascals plus, maybe 125 megapascals and a higher, and then high purity. But those 4 chapters we won't be able to talk to today due to the time restriction. So in chapter 1, scope, we have this figure, which actually I'm trying to improve. I'd like to put some offshore gas pipeline image in here to show where 31.3 and 31.8 actually interfaces on an offshore gas platform. But right now, these are the 4 figures we have in there. As you can see in the upper right, boiler piping that's covered under section 1 inside the boiler and out to the stop valve is not intended to be 31.3. That is covered by 31.1. But if you notice in the upper right, once you get outside the stop valves, the headers, the steam headers, 31.1 or 31.3, either one could be used. I've been at plants where some owners will run their headers, design them to 31.1. I've had others that will design their steam headers out in the plant to 31.3. That's the upper right. Packaged equipment. If you do buy a skid, a compressor skid or anything, the piping up to the skid and the piping inside the skid is intended to be 31.3. Once again, not on the rotating piece of equipment itself, but if you know how skids are put together, often with a pump, compressor, a heat exchanger, all that interconnecting piping is intended to be 31.3. I will say though at this point that it does depend on your local laws. Here in the United States, many states, we have Florida, Texas, California. Like for instance, California does impose 31.3, but not all states have a local law to impose 31.3. So it's up to the owner to tell the contractor that we want to use ASME B31.3. And lastly, if you look at the bottom 2, you can see piping up to a vessel or up to a compressor should be 31.3, but once you get inside it, you can see the very thin line there. It's not intended to be 31.3. And on fire tube heaters, the piping inside also is not intended to be 31.3. Okay, in chapter 1, which is our scope chapter, we define what the owner's responsibility is, paragraph 300B1. So the owner is the one that chooses the code of construction. The owner is the one that decides whether the steam headers should be ASME B31.3 or ASME B31.1. The owner also will determine the code itself is written around normal fluid service. So if the owner wants to impose either category D or category M rules, it's up to the owner to convey that information to the contractor. Otherwise, it would be written around normal fluid service. The material construction is also picked by the owner. The contractor may say, here's the specs we have, but once it's agreed upon, it was the owner's decision to say, yep, we want carbon steel or we want stainless steel. That responsibility stays with the owner. Same as the corrosion allowance is chosen by the owner. Once again, the contractor can suggest a corrosion allowance, but ultimately the owner is the one that chooses that. And then if you want high pressure rules or high purity rules to be imposed, the owner will decide that. And then also the owner provides an owner inspector. The owner inspector has to be the owner. It cannot be the contractor. Let's see here. The designer's responsibility. That's in paragraph 300B2. The designer is responsible to provide a code compliance compliant design. If there's cyclic service, the owner or the designer looks at the number of times the system is heated up and cooled down, or pressurized up and pressurized down. If it exceeds a certain number, the designer should be following the cyclic service rules. The flexibility analysis is the responsibility of the designer, and any additional requirements that is imposed by the owner that are contractual adders, the designer is responsible for. So if the owner in the contract says one thing, the designer should be following those. One thing the designer cannot be, though, they cannot be the owner's inspector. The owner's inspector has to be someone that has the interest of the owner alone in mind when they're doing inspections. And I'll talk about this a little bit later, but there's a difference between being an inspector and being an examiner. A lot of the individuals calling in ASME B31.1 are the examiners. There's situations that you can be both. If you work for the owner as an examiner, you can also be the owner's inspector, but you have to, as the owner's inspector, you have to have the interest of the owner in mind and no one else. The fabricator's responsibility is discussed in the scope section, again, chapter 1, paragraph 300B3. So the fabricator is responsible for procuring code compliant material, components, and perform workmanship according to the code. If the fabricator subcontracts out work, the fabricator also is responsible for that. And fabricators often will subcontract out work. But again, that fabricator who has a contract with the owner has overall responsibility for that subcontracted work. The fabricator is supposed to be doing the examinations, or at least responsible for the examination. And once again, if the contractor, the fabricator, contracts out that examination, the responsibility stays with the fabricator. All right. So the fabricator can't tell the owner that it's not my fault, it's the NDE company's fault. No, the responsibility still is with the fabricator. The fabricator is responsible for choosing an NDE company that will follow the code, and knowing the fabricator needs to understand that wherever's contracted out, that they're still have that overall responsibility to the owner to make sure the examinations are done properly. Leak testing is done by the fabricator and documentation. Once again, if that's contracted out and the piping tends to leak once you put it in service, the fabricator is the one that's responsible for that. Again, the fabricator cannot be the owner's inspector. And we'll get into that, the role of the owner's inspector. The owner has to have an owner's inspector. Let's talk about just a little bit. We also have roles for the erector, the manufacturer, and the assembler. They're all talked in paragraph 300B3. And in essence, they have the same responsibility as the fabricator in that they have to do erections according to the code. They have to manufacture parts in accordance to the code, and they have to assemble it in accordance with ASME B31.3. And any subcontracted work still stays with them. And once again, none of these can be the owner's inspector. There's a paragraph up in the scope that we often use quite a bit in interpretation requests. It's paragraph 300C3. The ASME Section 8 pressure vessel code has a similar paragraph called U2G. API 650 has a similar paragraph. Usually codes have this paragraph here that says more rigorous methods. And what it says in paragraph 300C3 in ASME is our piping code uses a simplified approach. And our code does not prohibit the use of design or construction methods equal or superior to the code. So you can do methods that aren't explicitly written in ASME B31.3 as long as that method, that material is approved by the owner and it's also documented in the engineering design. So often what we're talking about here could be an FEA. It could be a material that's let's see, a component, for instance, like a hose, a piping hose. We do not have a lot of rules here on piping hoses. So a piping hose manufacturer will use this paragraph here to allow to qualify those. So once again, it's take a look if you have a book, 300C3. It's a very powerful paragraph. All right, so some decisions that requires owner's approval. The designer has certain qualifications that they have to meet to design ASME piping, but the owner can exempt those if they feel like the designer's qualified enough. And we'll talk about that on the next slide. The owner also, if you want to impose the rules in design on occasional variation where you're actually exceeding the pressure rating of the pipe or the design stress by 120% or 133% for a limited number of hours, no more than 50 hours at a time during an event, and 500 for the year for the lifetime of the piping system. For the 133, it's 10% and 100. Then these occasional variation has to be approved by the owner. The rigorous design we talked about on the previous page, paragraph 300C3. And again, we're talking about FEAs. Any FEA like that, the owner has to approve the FEA, not the method. I won't say it has to approve the results, but they have to allow the designer, give them permission to say, yes, you can do an FEA on that. Again, the designer is responsible to ensure the FEA is done properly. If you want to use flammable fluid in plastic pipe, such as in PVC, polyethylene, polypropylene pipe, the owner has to approve that, but the code limits it still to 1 inch NPS. And lastly, if you want to pneumatically test plastic pipe, there's some pipe ABS used recently, high density polyethylene. If you want to do any of that pneumatic testing, it has to be approved by the owner, but the code does prohibit PVC, and CPVC is not permitted to be pneumatically tested. We talked about the earlier sheet on qualifications for the designer. Again, the owner can waive these, but without them waiving it, you can be a professional engineer experienced in piping design. You can have a 4-year ABET accredited college university degree, but you still need to have 5 years experience in piping design. If you have a 2-year degree or certificate, the code requires you to have 10 years experience. And if you have no degree or no certificate, ASME B31.3 requires you to have 15 years of experience in piping design. But once again, from the previous page, the owner has the right to exempt this, but this is the base rules for the qualification of the designer. All right, let's talk about fluid categories here. Again, the base code, we talk about normal fluid. The first 6 chapters are written around normal fluid service, which is flammable fluid, acids and caustics, fluids of those nature. If the owner, again, the owner has to decide that they want to impose category M fluid service rules. That's if something is highly toxic. Now, a lot of interpretation requests have come into ASME B31.3 and asked, is this a toxic material? And we do not define what a toxic material is. We often say water it can be very deadly. People will drown every day, but it's how you handle the fluid that is as important as what is the fluid. So category M, highly toxic. We do not give a list of fluids. The owner has to decide. Category M. I will say what I see a lot in owner specs, and I push back as a contractor. Often they will put acids and caustics in category M, but here at ASME, I put it this way, as the members on ASME B31.3, in their normal job as a contractor, they do not show acids and caustics. They do not design piping for acids and caustics in category M, nor flammables in category M. These are things that are phosgene. Certain gases are used in category M, but it's not typically flammables, acids, and caustics. Another category which you might be familiar with is category D, which tends to be what a lot of people call utility service, but it's more than just utility service. Any kind of benign chemicals. I used it as an owner one time when we made a polyol, which makes a polymer. The polyol is very sticky, very syrup-like. We would categorize ours as category D. You could stick your hand in the chemical, pull it out, wash it off, no problem. It was just a sticky material. So category D is not just utilities, which is steam, condensate, the ones that you're familiar with, but there's also benign chemicals that are non-flammable, non-toxic, not damaging to human tissue that can be category D. If you remember from a previous slide though, category D has to be decided by the owner. The rule though is it has to be limited to 150 PSIG. You can't exceed that. You cannot be designed for vacuum. It can't be colder than 29F or C, and it can't be any warmer than 186 C. That's the rules of ASME B31.3, but these are typical fluids that you see for category D fluids. All right. All right, the next so many slides, I'm going to talk about the stress theory behind pipe and why the formulas are in the code. This is a piece of pipe. It's a cylinder, as you can see. When you pressurize it, there's circumferential stress in the pipe, and the pipe wants to elongate in the long direction. If we slice the pipe in half, it would look like this, and you have two strips of metal that are holding the pressure in, and of course the internal chamber is being pressurized. At the end, you have stress around the circumference of the pipe. The pressure itself is wanting to, if you had a pipe cap here, is wanting to add stress in this. If you get what we call inloads, piping tends to be in contained, so you have longitudinal stress. Again, the metal around the pipe is being stressed, and the pressure inside the pipe is causing that stress. So looking at this a little closer, what you see is the pressure, this rectangle here is the pressure times the rectangle, which is a length of 2r times the distance dy. So this is the area that's imposing pressure, and that is being held back by the pipe, which is a thickness of t, a distance of dy, and there's two of them, as you can see when you take it in half. So that's where this term comes from, and that's the area that's resisting the pressure, and it's causing a stress in there. The energy, the pressure stress here is converted over to a metal stress. So this is what's called the equilibrium equation, and it's causing this hoop stress to occur. If you notice, there's some similar terms on both sides. So the dy's will cancel. And when you rearrange this formula, you get the thickness is equal to the pressure times twice the radius divided by 2 divided by stress. Or since we know the twice the radius is the diameter, we get the very infamous Barlow equation, T equals PD over 2SE. You see this often in the API 570 book. It's the basis behind sizing thickness in a pipe, and it's the basis behind the ASME B31.1 equation. If you look at the end stress, once again, you have pressure inside the pipe, and so that the pipe doesn't rupture, you have the circumference of the pipe holding it back. So the pressure inside the pipe is P times the area, which is pi r squared. That has to equal to the metal resistance. The circumference of the pipe is 2 pi r, but it's also times the thickness. So this is the equilibrium equation for the longitudinal stress. Once again, you see similar terms on both sides, so we can cancel pi. We have an r on both sides, actually an r square on one. So r cancels on one side, one of the r's. When you rearrange this, you get this formula. And since we know diameter is divided by 2 is the radius, we get the Barlow equation for longitudinal stress, PD over 4SE, a little different than hoop stress. If you remember, for hoop stress, it was PD over 2SE. So that's one fundamental principle in piping design, that the hoop stress is always twice as much as the longitudinal stress. And that's why when you do your flexibility analysis, typically it's you're just guiding the pipe. Your longitudinal stress won't govern unless you have a very poorly designed layout. All right, so here's the two equations. One is for hoop stress around it, kind of like your belt that you wear. If your belt is holding the circumference in, and then the longitudinal stress, these are the two equations, and they were developed 200 years ago by a gentleman in UK, Peter Barlow, and they've been around and they've worked for many years. It's principles behind all of the piping code and the pressure vessel code. Now, since then, those two formulas are based on stress theory. So a gentleman named Boardman came along and found out that this equation needs to be modified slightly. And you see this little YP factor in here. If you take this away, you get PD over 2SE. For longitudinal stress, you get PD over 4SE. But this little factor here just fine tunes the formula. It makes it a little more accurate. At low pressure, say 1 megapascal, 2 megapascals, you will not see a whole lot of difference. What we call a couple of mils, or in the metric, 0.1 millimeter, a very small difference. But these are more accurate in what's called the Boardman equations. And they were in the code until 2004, which we modified it again, and we added a W factor. All right. So the W factor came out of an incident 40 years ago at a power station here in California, the Mojave Power Station, that they had a main steam line fail. And what they found, that when they run at very high temperatures, that the weld actually will start creeping, will actually soften much faster than the pipe itself. So it's a factor that we put in the code in 2004 out of a couple of fatalities at the Mojave Power Station in California. And it doesn't come in unless you're in the creep range of the material. So for carbon steel, you're talking around 400 C. For stainless steel, you're talking maybe 500-600 C. So for most of the time, in a lot of applications, the W factor is just 1 and it goes away. So that's the equation in B31.3 for circumferential stress. And you can see it's very close to what Barlow developed 200 years ago, but we've modified it slightly based on things that we found out. All right. Excess hoop stress leads to fish mouth failure. Here on the right, you've probably seen this before. A pipe, when it's stressed, as long as the end welds are okay, welded acceptable, you will always see this longitudinal, this rip open in a long direction because of stress going around in a circumferential direction. It's ripping it open. And here's an example that you see every day in life. It might be a little comical here, but if you ever notice, if you grill a hot dog, it will rip open the long way. And that's what you're seeing, the hoop stress of the skin ripping open. So that is how piping will fail. And it's usually what governs the pipe design is the hoop stress. Now, what happens if the end loads are excessive? And this is an example of a tank that had a flat bottom. And in this case, the long seam did not rip open, but the circumferential weld failed. And it's called rocketing. So tanks often, if you overpressurize it and the emergency vent isn't sized properly, this is what you get. It will actually lift the tank because not the hoop stress, but the longitudinal stress was so great that it separated the cylinder from the head. So there's an example when the end loads actually failed before the hoop stress. This is a video that you can watch. It just shows a tank being rocketed by maybe 200 meters in the air. When these do fail, they do fly quite high into the sky at times. All right. So let's review what we just went over. Barlow's formula is very simple. PD over 2SE. Again, I'm an API 570 certified inspector. You see this equation all the time in 570. It's a very simple equation to use. It's more conservative. It will give you a slightly thicker requirement than these two here, which are more refined. So that's why we allow in ASME B31.3 to use this simplified formula. But again, we allow it because of this paragraph 300C3 that we've talked about, that the designer or the user of the code can use other methods equal or superior to the rules in ASME B31.3. Since these are the two equations that are in the design chapter, this one here is equal or more conservative than these two. So we use this quite often. If you want, if you don't have a calculator to do this, this is usually a formula you can memorize. And when you're out in the field, you rearrange it. You can actually design, if you know the thickness, many of you are inspectors. If you know the thickness, you can turn around and run this for your remaining pressure. So there's the three equations. The LeMay equation, very complicated, is based on ID. These two are based on D, the OD of the pipe. It's always asking for the OD of the pipe. The LeMay equation recognizes that when you look at, as pipe gets thicker, the ID of the pipe is stressed more than the OD of the pipe. So this little d is you enter the ID of the pipe, and then you actually enter it in the corroded condition. So this is a more complicated based on the ID of the pipe, and it's used in high pressure thick wall pipe. It's called the LeMay equation. All right. So once again, here's the three equations. Here's what each variable represents: the joint efficiency. There's the weld strength reduction factor. Again, only when you get up to a very high temperature does this reduce below 1. That's the W factor. Y is a factor that has to do again with the when you go from thin wall pipe, as the pipe gets thicker, this Y factor takes into account some through wall stress. Of course, we also add mechanical corrosion allowances. And again, the D here is the LeMay equation is based on the ID of the pipe, where the Barlow and Boardman equation is the OD. What's in bold here are the two equations that's in the code. Barlow equation is not explicitly written in ASME B31.1, but it's allowed again in paragraph 300C3. I use it all the time. I'll come up with a piece of pipe maybe 0.1 millimeters thicker, 0.1 millimeters. And since it is more conservative, we do allow the use of the Barlow equation. All right, I only have about another 10 to 15 slides and we'll take a break. So working pressure charts. We just went through the equations that are derived. We just derived the equations in ASME B31.3. And I've often had people, well, why do you need to go through all that when you have all these on the internet? You can Google working pressure. Here's one I did. That is the working pressure for 304L pipe. It even gives it to you in all the temperature ranges that we need in to do piping design. It gives you different schedules. It tells you the wall thickness, and it has all this working pressure. So why in the world would you ever want to calculate the wall thickness or the working pressure when I can just look it up? So here's why you can't rely on these. So this is one I found just last week. I threw it in the slide as, to illustrate an example. So that chart also had this paragraph below it. It said that ASME code for pressure piping 31.1, 1989 edition for welded pipe 312, a joint efficiency of 0.85. Allowable working pressures shown reflect the minimum wall thickness. So they even tell you that this is good for ASME B31.1, 1989. All these working pressures. All right. So why and sometimes you don't even get this with a table, but let me tell you why you need to be able to use the Barlow formula, PD over 2SC. For those workup tables that I just showed, and let me back up here, you can see they provide the allowable stress here, 13,003, 11,004, 10,002 at the different temperatures. So I went back and checked this, and sure enough, in 1989, here they are down here, 13.3, 11.4, 10.2. So they use the right allowable stress for 304L A312 pipe. However, if you look at the 31.1 allowable stress today, it's no longer 13.9. It's 14,200 PSI allowable stress. So that was the rule in 1989. In 1999, ASME decided that the allowable stress was too conservative, and they allowed a higher allowable stress when designing pipe. Now again, 304L pipe will yield at 25,000 stress, 25,000 PSI stress, and will burst at 70,000. So going from 13.9 to 14.2 was just a slight change into the design margin, and that was attributed to the better making of steel and pipe today. ASME decided as a committee, not just ASME, but the committee decided that we should allow the pipe to be stressed a little bit more. So these working pressures that I showed you no longer apply today. They would be much higher, actually. But just that's only due to allowable stress. Let's look at else what was wrong there. So that chart provides working pressures for very specific temperatures and pressures. They do not have corrosion allowance. So if you use that chart and the owner said, I wanted maybe 1 millimeter corrosion allowance, all those numbers would come down in working pressure. I'll show you here how to add corrosion allowance into the Barlow formula, into the Boardman equation. Those charts also do not have threading allowance. So that was for 3/4 inch NPS welded pipe. Often pipe at that size is threaded. So lookup charts will not have these two that will actually reduce the pressure rating of the pipe. They often, there can be a different mill tolerance rule. And I used 31.8 here is because 31.8, the gas pipeline, does not consider the mill underrun of pipe thickness. And we'll talk about that a little bit later. If you buy a Schedule 40 pipe or an extra strong pipe, and it says it's 0.432 inches thick, in 31.8, you get to use 0.432 inches thick. In 31.1 and 31.9, you have to subtract the mill tolerance, meaning the manufacturer at the mill may make that pipe, is allowed to make that pipe a little bit thinner than Schedule 40 or standard weight pipe. And we'll talk about that mill tolerance. So another thing is that happened to be welded pipe, the lookup table. But what happens if you have seamless pipe? That lookup table is no longer valid. Or what happens if you have dual grade pipe? That lookup table was for 304L. If you have dual grade, it also gives you a different allowable stress. And then once again, the safety factor, or nowadays we call it the design margin, changed in 1999 from 4-to-1 on tensile to 3.5-to-1 on tensile. So again, 1-to-1 on tensile would be the tensile strength of the pipe. So we still have a 3.5-to-1 margin on pipe design. Now with that, this I'm finding is a good time to take a break. But before we go on break, I do have a problem I'll show you when we get done with our Q&A. So do we have any questions up to now? And it will have an opportunity at the second break and at the end to also ask your questions.
Chip, what is the, how long do you want to have this break? 15 minutes is okay. It's okay for you?
Whatever you feel. I was thinking 10, but 15 is fine too. 15 minutes is fine.
No, 10 minutes it's fine. Okay. So let's do the following. We will be back on 10:55.
So real quick, as you go, this is the problem that we'll be looking at when we come back. Steam at 200 pounds, 400 degrees F, using this pipe, this corrosion allowance, threaded pipe. What wall thickness schedule should be used? This is something we will be working when we get back. If you want to look at it ahead of time, go ahead. So we'll see you in 10 minutes. All right.
Right. Thank you.
Thank you.
People.
Did you see a full screen?
Yes, we do.
Okay. All right. I think we left it here. My screen is changing, correct?
It's in the part. Yeah.
Okay. So just for those who are listening in, so you can manage your time. I think I've gone through 43 slides, and I have about 70, 80 to go. So we're at least a third, 40% of the way through. So here's the problem that I left you with. Again, in the first half, we talked about the Barlow equation, which is a theoretical derivation that was done 200 years ago on pipe cylinders. And that was the basis for the Boardman equation and the LeMay equation, equations 3A and 3B in the ASME B31.1 code. So here's a problem that I want to work out and show you how why lookup tables are often misleading when you trying to figure out a wall thickness or a minimum thickness or a pressure rating. So here we have steam, which is 200 pounds. It's got a design pressure of 200, a design temperature of 400 F. We're going to be using A53B pipe, which is welded pipe, electric resistance welded pipe. It will have a corrosion allowance of 1/16 of an inch. It's going to be threaded, and the question is what wall thickness or schedule should be used. So what you need to know first and foremost in this problem is what would be the S value, the allowable stress at these conditions. And so when I went back to table 1, which is in the appendix A in the back of ASME B31.3, I find a value of 19,900 for S. And also in appendix A, we have quality factors and says for A53B pipe, use a 0.85. And in this case, I'm going to use the simple Barlow formula. It will get us a answer that is for these conditions will be very, very similar to the Boardman equation. So the PD over 2SE will give us how much thickness we need for pressure. When I plug in the values of 200 pounds, the outside diameter here, so the outside diameter of 2-inch pipe is 2.375. This is, you use the actual diameter of the pipe, not 2 here. So in the Barlow equation, we add an S value here, which is how much you're allowed to stress the pipe. And then we use the joint efficiency of 0.85. So when you run these numbers for 200 pound steam, you find that all you need is 0.014 inches of wall for pressure. Now, how thin is 0.14 inches? It turns out that a piece of paper, that you would write on, what we call 20-pound paper, is actually 0.035 inches thick. So 0.014 inches of wall to hold 200-pound pressure. All you need is a pipe that's as thick as 4 sheets of paper. You often hear people refer to when something is thinning that it's as thin as a piece of paper. So in this case, when we do our calculation for pressure, we find out all we need is 0.14 inches for pressure. But that is not the end of our calculation. This is what you need for pressure. If you remember, we talked about a corrosion allowance. So this is metal that you need to design for that you would allow to corrode away during the 20-year life of the piping system. So in our problem, we had a corrosion allowance of 1/16 of an inch. So right away, our pipe wall thickness has jumped from maintaining only pressure to also a engineered corrosion allowance of 0.63. So now we're up to 0.77, much thicker once you add your corrosion allowance. Now here, we're not finished either. This is threaded pipe. So in threaded pipe, you have to account for the metal that's going to be removed during the threading process. And as you can see, a tapered thread where you might have wall back here, as it's threaded, you have less wall here. So we have to account for this mechanical threads in the code. Not for a welded piece of pipe, but welded, but for threaded pipe. And that's our problem. That was our problem, 2-inch pipe that was in steam that was threaded. So in order to determine how much metal is lost during the threading process, there's a standard, which is ASME B31.1, that will talk about tapered threads, straight threads. And what it tells you is that this height right here, or what you're removing, let's say, what you're removing is 0.8 times the pitch of the thread. This is in many machining handbooks too. When you taper a thread, it tells you that the amount that you're let me see if I can do this, that the amount you're removing, let's see here. Let me do one thing here. Trying to, there we go. And yeah, so the pipe is normally, it's not highlighting. So okay, so you're removing thread right here, and so how do we calculate that? When you have pipe and you're using a tapered thread, the pitch of the thread that they talked about was this 0.08696. I find this in a machining handbook. I believe it's also in the ASME B1.20 standard. And the pitch of the thread is the distance between threads. All right, now that information isn't that helpful, but what you also find here is how many threads per inch. And as you can see, in small pipe, there's a lot of threads per inch. And in smaller pipe, the number of threads per inch gets larger. This value right here is important to determine your threading allowance. It is, your threading allowance is 0.8 times your threads per inch, which is 0.8. And for 2-inch pipe, you can see this threads per inch is 11.5. So 0.8 divided by 11.5 is 0.70. So what that means is when you thread this pipe right here at the end, you have removed 0.70 inches of pipe. As you know, when a tapered thread has less wall down at the end than back at the unthreaded part. So you have removed the threading allowance in your calculation that will occur when you thread the pipe. And in this case, it's 0.70. So now where are we? So here's our formula. We had our Barlow formula equation, which said we only needed 0.14 for pressure. We added another 0.63 for corrosion allowance and another 0.70 for threading allowance. And now we're up to 1.47 inches required when we started out for pressure, a very small amount. So now we have pipe that's good for corrosion and we can thread the ends, but still we're not finished. So what it says in chapter 2, the design, is you also have to consider manufacturer's minus tolerance, because manufacturers can't make pipe perfectly. They're allowed to make it thinner, a little bit thinner, and the and the ASTM standard will determine how thin or thick a piece of pipe can be. So an example of that, if you buy 6 millimeter plate for something, you don't get 6 millimeter plate. You get 0.595 to 6.01. So the manufacturer has a range that they're allowed to manufacture their components to. And in the ASME 31.3 code, it says that you must consider that and remove it, because the pipe that you buy, and you will not be UT in it. You will get a mill test report that says this is Schedule 40 pipe, but it could be thinner than the actual published Schedule 40 thickness. So where do we find that mill under tolerance? For many of you that are API inspectors, I find API 574 has a table in it that collects the acceptable tolerances here for many pipes, like A53, A106, A312. These are very common pipe. And you could go to A53 and A106 and A312. It will send you to another ASTM on the manufacturing of the pipe that tells you that these manufacturers can make the pipe as thin as 12.5% less than Schedule 40 or Schedule 80. So if we know at ASME that the pipe might come in a little bit thin, we have to account for that. Now, inspectors that I come across, they have this number memorized, 12.5%, 12.5%. And that is true for some very common pipe, A53, A106, A312. There's a few more there. However, if you look at this table, A134 and 135 and A358, this is road stainless steel. You make pipe out of road plate. I've used this before. It doesn't use 12.5%. It says your mill under tolerance is 0.01 inches or 0.03 millimeters. So you can see it's no longer 12.5% for all pipe. It turns out here that A135 uses the 12.5%, but some of these other ones, if you happen to buy A451 pipe, it says that it comes in 0 under tolerance. So there's nothing to remove. You would be done in that calculation. But for us, we were using A53 pipe. So we have to account for this 12.5% wall reduction because we might get a piece in our system. Furthermore, on mill under tolerance, I want to point out, these are all piping standards. A587 is a pipe that was developed years ago. I believe DuPont did that to allow you to code bend pipe, take straight pipe and bend it, and it won't stretch. It will stretch, but it won't overstretch. So this was a very specific pipe spec developed by a US company years ago that allows you to code form pipe and bend it without it wrinkling. And its mill under tolerance isn't even in A574, this table. Where you find it is here in a different table that says A587, the mill under tolerance depends on, like for instance, if we had 2-inch, the nominal is 147, it says they can make it as thin as 135, which would be 12 mils. They could also make it as thick as 159. And then if you happen to buy a thicker version of 2-inch, a nominal 208, it tells the manufacturer they can make it as thin as 191 or as thick as 225. So this mill under tolerance in pipe, ASME B31.3 and the upcoming presentation 31.1 requires you to account for this mill under tolerance. As a side note, which we're not going to be doing today or tomorrow, 31.8 does not require you to remove this mill under tolerance. And they have their reasons why, but for now, let's just say 31.3, 31.1, you do have to account for this mill under tolerance. And I'll show you how we do that. So back to where we are on problem 1. We had 200-pound steam at 400 F. We had some corrosion allowance, and I wanted to be able to thread my pipe. So I have an 014 wall requirement for pressure, an 063 for corrosion, an 070 for threads, and I ended up with an 147. Now, because my pipe might come in 12.5% thinner, I have to make this calculation, which I can only take credit for 87.5% of what the final thickness is. I set that equal to 147. I divide the 2 by 0.875, and what I get is a final T required of 168. We've gone a long, long way from a pressure requirement of 014 to what ASME B31.3 says you need to design for, because a corrosion allowance, threads, and mill under tolerance kept stacking that requirement up. Now, 168, the question is, at T equal 168, do I need schedule 40 or do I need schedule 80? So when I go to a pipe wall schedule, you can see that at 2-inch at schedule 40, it's 154, and I need 168. So it tells me I need to buy schedule 80 pipe if I want to thread 2-inch pipe with a 1/16 of an inch corrosion allowance. Now you can see we're just barely over the 154. We're at 168. We're 14 mils over. So the corrosion allowance that was added bumped us up to schedule 80. The corrosion allowance is something that is set by, say, a metallurgist based on predictive service. And myself, I find that often overspecified. Too many times somebody wants to throw stainless steel with some corrosion allowance, and a 1/16 of an inch is quite a bit of corrosion allowance, in my opinion, for stainless steel. Typically, you won't experience uniform metal loss. Stainless steel will stress corrosion crack, and all the thickness in the world won't prevent stress corrosion cracking from occurring. So it's an example of just by overspecifying the corrosion allowance, you might have cost the piping system a little bit more than it needed to be designed for. So that is how you go through and build up and determine a wall thickness based on a particular application. Again, the lookup pressure charts that we were using did not have threading allowance. It did not have corrosion allowance, but it did account for the manufacturer's mill underrun, the tolerance, and it also accounted for the pressure conditions and the code of construction. So this is the reason why we need to be able to calculate a T minimum. And for hoop stress, I just showed you how to do it. Now, when does span govern? So when does hoop stress no longer governs the wall thickness, but the slope, the sag in the pipe might govern the wall thickness. And that is the longitudinal stress. All right, if you remember, the Barlow equation for circumferential stress was divided by 2 SE. For longitudinal stress, it's divided by 4 SE. So this equation would not apply. But so let's use example where we have nitrogen. We have 80 pounds. We're running it at 125 F. It's seamless pipe, A53B. Again, A53B is one of those pipe specs that comes either ERW or seamless. So you need to know that. Being nitrogen, I'm going to put on 0 corrosion allowance, although you do have to be concerned with, say, for instance, corrosion under insulation. In this case, it's nitrogen at low temperature. I don't anticipate it being insulated. It will be painted. It's in a dry environment, so I applied 0 corrosion allowance. And in this case too, I'm going to butt weld it, so I don't have to worry or calculate about the thread allowance in this system. So when I go back in the back of Appendix A, Table A1, for A53 pipe, I find it to be 20,000. I find a joint efficiency of 1. So in this case here, this should be a 4 here, my mistake. No, I think, hold on a second. No, let's go through a pressure. I'm going to go through and calculate what pressure would be. So pressure on hoop stress would be PD over 2SE. Here's all our terms, but again, we know the corrosion allowance, the mill tolerance is 0, mechanical allowances, so the pressure alone is 0.006. Now, if I went to a standard wall based on pressure, I can see that once again, 0.006, I could go as low as Schedule 5 pipe, 0.006, right? 0.006. Now, once again, if this was longitudinal stress, this is divided by 4, and in the longitudinal direction, the end is 0.003. So stress on a pipe is going in 2 directions. I only need 0.003 for the long direction, 0.006 for the pressure direction. All right. So, but I'm going to show you where, even though the pressure is 0.65, that why Schedule 5 pipe would not work in this application. So one thing that the ASME code will have you do through the flex analysis is determine if there's if the pipe is sagging too much. Now, without going through a flex analysis for this workshop, what I did was I went to the back of, again, API 574, which uses guidance for in-service. And for 2-inch pipe, it tells you that for structural strength of the pipe, the structural, which is the long direction, you should have at least 70 mils or 0.07 inches, 1.8 millimeters for the structural strength of the pipe. And they set an alert at 100 mils or 2.5 millimeters. So for pressure, where all I needed was 0.006, and once again, since I had no corrosion, or this is all I would need for pressure, I know for structural strength, I need at least 70 mils for structural strength. Again, I didn't want to run a formal flex analysis, so I looked into 574 and see what that said. And so if I add my alert level of 100,000 over here, and again, this is for carbon steel, it says that I should start out just for structural a 106. And so in this case, this pipe would say it only needed 0.006 for hoop stress, but it's going to need 1.06 for longitudinal strength. So here's a case when span governs. And for 106, you can see I would not use a Schedule 5 pipe. I would use a Schedule 10 pipe, minimum 106, because the Schedule pipe is 109. And actually, if you look at 109 and take the mill under tolerance, which I know is 12.5%, that would actually bump me up to a Schedule 40. So that is why for nitrogen at 80 pounds in the plant, you often see a Schedule 40 pipe. It's not for strength, but it's for structural strength, or it's not, I should say it's not for pressure stress, it's for structural strength. So that's when span governs. When you have a low pressure application, you tend to have small bore pipe, say under 4-inch NPS, and you have no corrosion allowance, or low corrosion allowance, your span will govern, and not your pressure. So again, I only needed 006 for hoop stress. I need 106 for structural. All right, let's move on. Let's talk about branch connections now. Often you see branch connections stabbed in to a header pipe like this. And I hear a lot of people say, oh, you can do it all the time. That's not the case. When you put a opening in a pipe, it will weaken the opening. And so ASME B31.1 requires you to check the strength around the pipe. Let's see here. I want to see. Yeah. See if I can do something here. Yeah. All right. So sorry. So here's the branch connection. It's a 2-inch branch. Here's this was a 1/2 inch that I happened to be out in the field. So in the design part, chapter 2, it will have you this very complicated figure. I'll walk you through what it means. It will help you determine whether you can stab the branch in, whether you need a repad, whether you should use a coupling or an OLET. So in this branch connection calculation, you see a lot of stuff going on here. This bottom is the header, and this is the branch. What's going vertical is the branch. They also happen to show this branched in at an angle they call beta. A lot of these, this is 90 degrees. So beta is 90. And when you run this 2 times minus the sine of beta, this area here becomes this goes away, the angle. 2 minus 1 is 1. So it says multiply this area by whatever this formula is. So 2 minus sine of 90 is 1. So this area that's back hashed through here is the area that you can see when you look down the center of a branch. And this area here, you have to make up in metal, extra metal around the branch connection to determine whether or not you need a repad. Now, how do you do that? So this area here, which we call A1, is not the thickness of the pipe. If you notice here, the pipe over here has this hash and several hashes. What these bottom 3 is the corrosion allowance, the mill tolerance, and the pressure stress. So I'm sorry, is the mill tolerance, the corrosion allowance, and what's left is this hashed here, which is how much of the pipe is needed for pressure. This cross hash here. So this area here you have to calculate. It's a distance. It's a length times a width, and you have it on both sides. And there's a rule in the code that says you can only go out D2, a certain distance here. You calculate how much metal is, how much metal here that is being used for pressure. You're calculating how much is used for mill tolerance, how much is for corrosion. And what's left is for reinforcement is this very thick hash. This number right here is A2. It's not much. It's not much. As you can see, there's a little bit of extra metal in pipe that's not used for pressure. It's not used for corrosion. It's not used for mill tolerance. It's extra metal because you bought your pipe as Schedule 80. You didn't need all of Schedule 80. So some of that extra metal is there for reinforcement. It's to make up what you take out when you put a branch in a header. So we have extra metal here in the header. We have extra metal over here, and it's out a distance D2. This D2 is essentially, if this is a diameter, a 2-inch branch, you're allowed to go from the center out 2 inches, and whatever this area is, past the opening and into the header, you calculate T times a distance. You also have some extra metal in the branch. If you look at the branch connection, you have a pressure, something that we calculated based on Barlow formula. We have a corrosion allowance. We have a mill under tolerance. And this big heavy hash mark is extra metal in the branch. So we have extra metal in the run pipe, in the branch. And as you can see from here, this area, these 2 areas, and this likely doesn't make up the area removed there. This is a mathematical calculation you have to do. Software does it quite well. And so if we don't have extra metal in the branch in the header, then you have to add a repad, what's called A4. So again, we have an A1, the area where we remove. We have an A2, extra metal in the run pipe. We have an A3, extra metal in the branch. And if that's not big enough, we have to add a repad. So what that says is we've moved an area, and that area has to be, actually this should be less than. This area we remove has to be less than A2 and A3. So whatever we move here has to be a smaller number than what's available in A2 and A3. Otherwise, we add a branch. All right. Now, if it does happen to be smaller, if we have a lot of extra metal in the branch, a lot of extra metal in the header, then you can just stab it in the way we did here. You can just stab it in. You have plenty of extra metal around the nozzle in the header. You have extra metal in the branch, and it's greater than what you see down the center of the pipe if you happen to look down the center. And in this case, I actually went back. This was an existing piping system built 40 years ago, and they asked to re-rate the piping system from 80 pounds to 180 pounds, or from a 0.5 megapascal to about 1.25 megapascals. And so I went back and I checked the reinforcement around the branch here and found that this stab-in branch connection that was good for 80 PSIG is also good for 180 PSIG. So that's how a branch connection calculation's done. There's 3 things I can do. If it's not adequate, I can add a repad. But many of you all see in the field OLETs. An OLET is by code rules self-reinforced. What we're saying is no matter how much area you take out here, the OLET is thick enough to account for this metal. You don't need a repad around an OLET. Or if you happen to use a B16.11 ASME B1611 coupling, a socket coupling, a threaded coupling, those can be self-reinforced too if you choose the right pressure class. So, all right, in this case, the stab-in nozzle was permitted. Here's again a picture of the what the exercise we went through. You have to calculate A1. It's this thickness times this distance. Length times width, it gives you an area in square millimeters. Here's some extra metal in the header pipe. Metal that's, if we chose schedule 40, schedule 80, we always know from the Barlow formula how much is needed for pressure. We know if we had a mill under tolerance. We also know if we have a corrosion allowance right here. So this is extra metal right here, which is called A2. So again, this is something that's handled where with software. It could also be done by hand though. All right, so there we talk about the OLET and the fittings. One other thing in the field that I feel helpful is here's an example problem I want to go through about thermal expansion. It's also in table C1M in the back of ASME B31.3. And this is for group 1 carbon steel material. I've highlighted a few things on here. And what I've highlighted is this is how much pipe will grow given a certain heat up. So in this case, I'm taking pipe that's maybe at 20 C, and I'm going to heat it up to 50. And it says, it gives me this coefficient of 0.4. And in another application, I'm going to take 20 degree pipe and heat it up to 150, which might be like a steam header. And it gives me this 1.6 factor. Again, this is table C, 1M in the back of ASME 31.3. So in this example, let's say you're over installing a small water tank that's horizontal. It's got 2 saddles. It's 5 meters long, the tank. The saddles are 5 meters long. And you know you're going to put warm water in there that will heat up to 50 degrees. And you know that the tank was installed at 20. So what this says is if I use this factor of 0.4 and the distance over 5 meters, it will grow 2 millimeters in length. All right. So I don't find 2 millimeters growth to be very concerning. The bolt holes will be drilled larger than the bolts. So for a tank like this, that's going to warm up 30 degrees C or even cool down 30 degrees C. These values go the same in the opposite direction. They're providing them at minus 50 C, minus 100 C. But again, if it's cooling, then let's say you install the tank in a very warm climate and in the winter it gets cold, it will then shrink by 2 millimeters. Now, that's not very concerning, but what is maybe a steam piping that heats up to 150 degrees C. And let's say it's a very long steam pipe. So the next example, I have a 50-meter long steam pipe, and it's heating up to 150 C. As you can see, over that distance of 50 meters, which is not very far, it is going to grow 80 millimeters. So this table I find very helpful if you're in the field, to get some kind of idea of some of the very long piping runs, how much that it will grow as you heat it up. Just wanted to share that with you. It's something that I hear often in meetings. A small tank, they're worrying about it growing too much. Now, in case like a small boiler that might go from 20 degrees well up over, say, 200 degrees, you can see even a small boiler will grow quite a bit. If you take this to 0.4 up to 2.0, now it's going to grow 5 times more. Now we're talking the boiler will grow 10 millimeters, nearly a half of inch. So this can be used not only in piping, but it can also be used in equipment, anything that heats up and slides. All right. That is concludes my presentation on the design part of ASME B31.3. I want to move on to chapter 3, which is materials. And materials, there's 2 big groupings, what we call listed materials and unlisted materials. Now, what are these listed materials and unlisted materials? A listed material is a material that you'll find in the ASME B31.3 book, and it's found in Appendix A, our stress tables. It's in B, which is the non-metallic tables, and K, which is your high pressure tables. Now, when you go back to Appendix A, you will see a list of all these ASTMs that are pre-approved for use. I just took a small snapshot of it, but these are what we call listed materials. They are pre-approved to be used as is. A53 pipe is one that we, as the committee, we've pre-approved that. So what's, well, here's another slide that shows you that when you still in that table A1, not only do we show the materials, but we're also giving you allowable stress values back in appendix table A1. So that's the good thing about using a listed material, is the ASME code provides you the S value in the S value to do your bar load quick calculation. Now, also Appendix B has a picture of the non-metallic pre-approved materials: PVC pipe, polyethylene, ones that are made to a certain ASTM. We provide the allowable stress. These are called listed materials, and they're much easier to work with as opposed to an unlisted material. Appendix K, again, that's the high pressure. The list of materials that are used in the high pressure is very limited. The piping components are very limited. For instance, A134 pipe, A135 pipe, some of those are not allowed in Appendix K. This is where you're getting up to a very, very high pressure, upwards of about, let's see, 17 megapascals, 17 megapascals. So what's an unlisted material? So an unlisted material is a material that's not listed in Appendix A, B, or K. Now the code, ASME 31.3, has rules on how you can use an unlisted material. And it says that an unlisted material may be used provided they conform to a published specification that covers chemistry, physical and mechanical properties, method and process of manufacture, heat treatment, and quality control, and otherwise meet the requirements of this code. In other words, if we have welding requirements, your unlisted material needs to be weldable. We also go on to say that the allowable stresses shall be determined in accordance with the applicable allowable stress basis of this code, or a more conservative basis. So the difficult with unlisted materials is you don't have these S values. And if you're going to have a material, for instance, like, let's say a new hastelloy material is developed that's not in the code, then the manufacturer of that or the user of that has to determine what is its allowable stress at 300 F, whatever temperature you're using it at. So most material manufacturers would like to get their materials into the code, and that way they get widely used. Listed materials, again, are pre-approved. They're used very easily. Unlisted materials are permitted, but you have to go through a little bit harder process. ASME does not do this, You, the designer will determine how to approve an unlisted material following these rules here. Now, ASME also allows you to use reclaimed materials. So if you want to use used piping, you can do that. However, it does say that it needs to be cleaned and inspected and shall determine the minimum wall, and it should be free of defects. What ASME doesn't allow you to do is use an unknown material. So if you find a piece of pipe and you want to reuse it, you have to be able to identify its strength. You have to be able to know that it's an A53 pipe, or that at least had a tensile strength equivalent to A53 pipe, because as you know, a lot of reclaimed materials will no longer have the manufacturer's information on it, but you can reuse it as long as it's got the minimum thickness and it's acceptable for the intended service. All right, so moving on to chapter 4 is we're going to talk about listed components and unlisted components. And once again, just like listed and unlisted materials, It's much, much easier to use a listed component in ASME B31.3 than it is to use unlisted components, but we do allow unlisted components. And let's look at that. So a listed component in ASME 31.3 is any component that's in table 326.1. So I've taken a little snapshot here in the code, and as you can see, B1611 couplings, forged fittings, socket welded, threaded couplings is what we would call a listed component. Also, B16.5, this is where you use a flange. An ANSI class 150 B16.5 flange is a listed component. Here's where you find B16.9, which is your butt welded fittings, your T's, your elbows that are butt welded. So all these, it's a much longer table than what I've shown here, are what's called listed components. They are pre-approved by ASME B31.3 to be used according to the published values in these standards. No calculation is required. Use them based on the pressure temperature rating of the standard. Now, here's some other listed components in this table. There's some MSS fittings. Again, this table is a couple of pages long. I've only taken a few little snippets of it, but get familiar with table 326.1 because those are all your listed components, pre-approved, used according with the pressure temperature limitations of the standard. Gaskets, again, your metallic gaskets, your spiral wounds, your spiral wound right here, your spiral wound are shown in B16.20. So when a manufacturer says that we are providing spiral wound gaskets in accordance with ASME B16.20, the piping code says you're good to use it as is based on any restrictions that B16.20 would have. So here's one thing I wanted to point out, the flexible hose. We don't have a lot of rules, a lot of listed components for hoses. They will treat it as an unlisted component, which I'm about to talk about, but we do allow this British standard 6501. If you have a flexible metal hose, and if you follow, there's a couple of notes here that you need to read. There could be some restrictions on this, but if you have a flexible metal hose and it's made to BS 6501 Part 1, you're allowed to use it without any other qualification based on the restrictions that the hose manufacturer, the standard tells you to. Most hoses are not in here. It's treated as an unlisted component, and also many expansion joints are not listed components. The expansion joints you see out in piping systems. We'll talk about that. So what is an unlisted component? An unlisted component is a component that's not in table 326.1. So if you don't find a manufacturer making a component to one of these standards that are back here, the piping code treats it as an unlisted component. Now, what do you do with an unlisted component? A hose that's not made to BS 6501, an expansion joint. How do you qualify those to be used in the ASME piping code? We have a paragraph up in the design section that says you can use it, you can qualify an unlisted component if you meet one of the following 4 conditions. One is extensive service history. And where you use that is if you happen to have a component that's used, say, in another industry, and I'll give example, we use this very large flanges, like ASME B1647 only goes up to, I believe, 60-inch flanges, NPS 60. And sometimes in the American Water Works Association, you'll find 120-inch flanges, very large flanges. 120 inches is 10 feet, 3 meters. And so So if you wanted to use a flange that is not listed in B1647 that has a pressure rating and has extensive service history, this is how you would use it under paragraph 304.72a. And I have a picture coming up of a very large flange that would be outside the B1647 standard that would be qualified possibly under this clause here. Another thing, you can qualify something using experimental stress analysis, and that's where you stress something and you analyze it under certain lenses to see where your stress points are. You can do a proof test. You can make something, you can pressurize it up to a point where it fails, and then you apply a safety factor. So dimples, I do know, like for instance, on jackets, on vessels, like a dimple jacket, it's a very odd geometry. A manufacturer will make a dimple jacket. It's the method is done the same here, where they make the jacket, they pressurize it. It might fail at, say, 3 megapascals or 4 megapascals. And they say, okay, if it failed at 4 megapascals, we have a 3-to-1 safety factor. So you can only design that to 1.3 megapascals. So proof testing is a way of making an identical component, pressurizing it, letting it fail, and then applying a safety factor. And finally, which is done often, is a stress analysis or an FEA. So if you have something that's an unlisted component, again, it's not listed in table 326.1, a manufacturer might do a stress analysis and say, yes, the stresses are low enough that we can qualify to 31.3. Now, ASME B31.3 doesn't approve, pre-approve, or endorse any component out there that's unlisted component. The manufacturer of that component is certifying that that code material, that unlisted component meets ASME B31.3. That's one of the requirements of that manufacturer to certify it. And as an owner, I would always ask them for some certificate of conformance. It doesn't come from ASME. The certificate of conformance doesn't come from ASME. It comes from the manufacturer. It's their attesting to you that we have gone through paragraph 304.72. We have followed the rules right here for unlisted components, and they're giving you a certificate saying that this expansion joint, this hose, anything that's not listed in table 326 that you want to use in an ASME piping 31.3 system is certified. And again, it's done by the manufacturer. All right, so that's a very powerful paragraph that's used for unlisted components. Anything that the design rules don't cover, paragraph 304.72 allows you to do basically proof testing, stress analysis, things like that to qualify the system. Here, I'm going to run through an example of an unlisted component. This expansion joint is not in table 326.1. Here's the example 2 of some very large flanges, as you can see. They would be outside the B1647 size limits. So here's one component that would be unlisted. Here's another one. I'm going to walk through some of the rules on how a manufacturer would qualify these components. So here's the expansion joint where the manufacturer actually did an FEA on the metal part. Okay. As you see, the expansion joint, it has a metallic portion and it has a rubber portion. You have to make sure that nothing in here gets overstressed. So they were able to do the FEA on the metal portion, and they found it to be within ASME design margins. And they also then did a proof test to verify that the rubber is strong enough. And looks like we're done for a second break. So this is how you would qualify an unlisted component. So I don't have an exercise at this break, but I can tell you we're about 85 slides into it and we only have about 30 to go. So if we can take one final break, when I come back, we'll go to part 2 and part 3, which is going to be, let's see, working with best practices. All right, 10 minutes, is that okay?
Yeah, 10 minutes, it's okay. So
Okay.
we'll be back. Let me check here. 10 minutes past noon.
Okay, we'll be back.
We can go back.
Okay. So do you see my screen?
Yes, part 2, best practices.
Okay. All right. I'm just for those that are watching the time, this is slide 87 or so, 89, I think, something like that, out of 117. So I only have about 28 slides left. We've gone through about 90 slides. So best practices, we'll conclude with best practices and code changes that we've made recently and we're looking at in the future that would be beneficial to know. So this last 28 slides, what we'll talk about is best practices, which is, we're going to look at chapters 5 and 6 of the code, which is fabrication, assembly, and erection, which is 5. And then chapter 6 of the ASME B31.1 code is inspection, examination, testing. Then that one, I'll go into a lot more detail. I'll talk about the difference between inspections and examinations. I'll talk about the role of the owner's inspector. And also, I'll get into some testing requirements, how to calculate hydro test pressure, things like that. All right, so for chapter 5, which is fabrication, since this workshop is more around examiners and all that, I've only have one slide here for fabrication, erection, and assembly best practices. One thing is the 16th-inch socket gap. We get a lot of interpretation requests on that. As you know, if you socket weld, if you use a socket fitting or a socket flange, you put the pipe in, you back it off 1/16 of an inch, you make a mark line, welder welds it, and we get a lot of questions about that 1/16 of an inch. How accurate does it need to be? And we continue to answer this to users that say that it's just an approximation. If it ends up being 3/8, closer to 3/8, we don't find that unacceptable, but we're working on a change to help improve that rule. We also get a lot of interpretations to find out after do they need a radiograph that socket when they're done and verify that there's a 1/16 of an inch socket after welding. And so we've answered that said no, once it's inserted, you back it off approximately 1/16 of an inch, you weld it, and that's it. So that's a much discussed rule in the piping about that 1/16 of an inch socket gap. I guess what I want to emphasize, it's not meant to be it's not even meant to be a documented number. It's meant to be some guidance. When you weld the pipe, it's going to expand a little bit into the socket. And we just find a 1/16 of an inch approximately. It's in the code, but it doesn't, seems like it gets a lot of questions. So it's something we're working at the committee to try to improve that language. So let's see, okay. So that's another thing that we get a lot of interpretation requests on is number 2, spools can be leak tested in the shop and only required an in-service test when assembled into operating position. So you see that a lot on fabricated spools that they're hydroed in the shop. And the question comes up, don't I need to do another 1.5 hydro in the field? And we continue to answer that as no. It already satisfied the code requirements by doing testing the subassembly, but we do require some kind of in-service leak test once it's in the operating position, but it doesn't have to be at the 1.5. Another thing that I want to point out is in 31.3 is welds can be painted before leak testing. This is a rule that 31.1 does not have. 31.1 prohibits welds to be painted before you leak test them, but they also allow 31.1 allows you to insulate your welded joints during hydro test. 31.3 takes the opposite on those two. We say that welds can be painted, but I say in number 4 that the welds cannot be insulated. So you have to visually verify the leak test. Though I will point out number 3, many owners will write into their specs that says that the welds shall not be painted. So in that case, if the owner has a contractual requirement to say don't paint the welds, then you shall follow that and not ASME B31.3. Because the owner can always add requirements, more conservative requirements to a piping system. They just can't take one away. If you remember my earlier interpretation, I asked in normal fluid service, can a leak test be waived if the owner approves it? And I said no. So the owner can always add more safety into the code, but they can't take away safety and still meet 31.3. So another thing that is in fabrication that's a best practice is your flange assembly. We do reference ASME PCC1, which is a recommended way to bolt up a flange. But I'll point out here that it is something that we don't make it a requirement. We only make it a recommendation in Chapter 5. And I'm finding more and more owners are actually following PCC1 when they're bolting up flanges. So that's just 5 items I wanted to talk about best practices in Chapter 5. And again, some of these we're constantly looking at to see if this is good for industry, good for safety, and whether or not we need to make any changes. And number 1, the 16th inch gap is one that we're looking at very closely. We actually just put through a code change that's going to be in the 2020, no, it's going to come out in the 2022 edition that will explicitly say that those socket fittings do not need to be radiographed after welding. So, all right, moving on. The inspections versus examinations. I guess the one thing I want to emphasize here is inspections in 31.3 is performed by the owner. Examinations are performed by the fabricator, the assembler, or the erector. Now, the one exception to this is if the owner does their own fabrication, assembly, or erection. So in other words, if Petrobras wants to have their own employees weld up a piping system, then Petrobras can do their own examinations. But if they outsource the fabrication, then the examinations would be the responsibility of the fabricator or the assembler or the erector. So that's a big difference. A lot of times we talk about fabricators doing inspections, and that is, I won't say it's from a code standpoint, we say the owner does inspections, the fabricator, assembler, the erector does the examinations. And I'll use some examples coming up here. So the owner's inspector, here's some requirements by the owner inspector. Number 1, the owner inspector provides QA oversight to ensure the piping system is being fabricated, assembled, and erected to B31.3. No, now, the owner's inspector provides the QA oversight. And I made a note here that says it's the fabricator that's responsible to perform the documented QC activities. So in other words, if there's a requirement to do 5% radiography, the fabricator needs to keep track of the welds, keeps track of the welders, and make sure that the 5% radiography rule is met and that all the welders in the lot are represented in that 5%. And the owner's inspector merely has the right responsibility to check the fabricator's documentation. So item number 2, the owner's inspector is not required to read film, witness hydro test, or verify fabrication is being performed properly. That's not the role of the owner's inspector. The owner inspector can read film and all that, but it's the fabricator's job to do those examinations. Now, if we got an interpretation request from ASME that said the film was read by the fabricator and accepted it, but the owner did not think that it was correct, we would say that that's a contractual issue because the fabricator has the responsibility to read the film and accept it. Now, the owner inspector has to make sure that examiner is qualified. Again, the owner's inspector may not even be qualified to do any NDE method. If you see number 3, I myself have been an owner's inspector before, and I'm not a level 1 or a level 2 in RT, PT, or MT. I do not have qualifications to do examinations, but yet I could still be an owner's inspector and go and review the fabricator's documentation to make sure that the fabricator is fabricating pipe in accordance to the rules. So again, that's the role of the owner's inspector. And we also want to say here, I have a couple of more things here. The owner's inspector determines how much QA oversight is needed to ensure. So we do not say that the owner needs to look at all the documentation. Now the fabricator needs to look at all the documentation. They're generating the documentation, but the owner's inspector just needs to look at stuff to ensure the fabricator or the assembler is doing the right job and that they are doing it in accordance with B31.3. Another thing is B31.3 does not impose any time requirements on when owner inspections are performed. So you might ask, do you see this often? An owner's inspector might come into the shop after half the piping has already been fabricated. After half the piping has already been fabricated, it's not good practice. ASME B31.3 doesn't say when the owner's inspector should be involved, only that the owner's inspector has a role. So if the owner inspector gets to the piping shop after half of the piping has been fabricated and finds a problem, ASME does not get involved. That's a legal dispute between the owner and the fabricator, and somebody else will settle that. All we say is that the owner's inspector has a role here to oversee, to do a QA function of the fabrication. All right. We actually got an interpretation request a couple of years ago. The owner's inspector came in when it was all complete. It was all complete and found some things they didn't like. And it ended up going to ASME. We said, we do not issue when the owner's inspector does this, other than that's something that the owner and the fabricator has to work out ahead of time. When are your hold points? When are any things you want to come in and witness? All we say is that the owner does have a role So that's that. All right, a couple of things I want to talk about on ND examination under general requirements is we do say in paragraph 342.1 that your examiner shall be qualified in accordance with the boiler pressure vessel code, section 5, article 1. So your RT, your PT, your MT, all need to be qualified to section 5. We also say that the ND personnel cannot examine their own production work. So if you happen to have a very skilled person that can read film and can also weld, that person cannot weld up their joints, shoot the x-ray and read the joints and say, yep, my welds are good. So the ND personnel cannot be examining their own production work. We say that in 342.2. The ND methods, which are, PT, RT, VT, we ask you to follow section 5. Let's see. The NDE acceptance criteria for how much slag or imperfection is in a weld, or is a crack or is underfill allowed in a weld. That acceptance criteria is not found in section 5. It's found in the Code of Construction, B31.3, chapter 6. For instance, in our code, we allow a lot more, let's say we allow some imperfections that would not be allowed, say, in the pressure vessel code. We're allowed, let's see, so the acceptance criteria, what you need to remember is typically in the construction code. And in ours, it is in chapter 6, 31.1 has theirs. Section 8, section 1, they will have their own acceptance criteria as what's an acceptable defect. So again, we're still on 31.3. 31.3 does something that some of the other code doesn't book. We do not, like in 31.1, they'll either won't x-ray or they'll x-ray the whole piping system. Same way, we actually have a percentage-based examination requirements, and that percentage is randomly chosen. So the rules are, as many of you that use the book are well aware, that we have a 5% RT requirement of circumferential butt welds. We also have 5% of any braze joints. Since you don't x-ray a braze joint, we have what's called an in-process examination procedure, where you have a multiple step process of how to prep the joint, how to clean the joint, how to braze the joint, how to inspect the joint. So since you don't have radiography on braze joints, we do have a 5% rule to do in-process examination for brazed joints. And we have a 5% VT visual requirement of all fabrication. That's not just welds, that's threaded connections, even flange bolt ups. There's a 5% visual verification for fabrication. Now that is done, once again, these are examinations. So these are not done by the owner's inspector. This is done by the fabricator. Or if the fabrication was done in a shop and sent to the field, and you have a different erector than the fabricator, now the erector has to document 5% of the fabrication met the code, or 5%, I'm sorry, of the assembly met the code. There are some assembly requirements. We do talk something in there about flange fit up, a certain acceptable amount of misalignment on the flanges. So that's on, that 5% is on the assembler and the erector in this case. Now, because as we do these examinations, we might find a defect. We might find something in a weld that's not right during fabrication. We might find a threaded pipe that wasn't threaded properly. Perhaps it leaked in the field during a hydro test. So we have something called progressive sampling, paragraph 341.3.4. And this, again, this is performed by, these are all performed by the examiner, not the owner's inspector. So progressive sampling, if I have yeah, I don't talk about it in depth, but that's where when you find one defect, you're required as the fabricator to go into that defect and look for 2 more of that, say, welder's weld, and x-ray that. Because we only had a 5% requirement here. Now you have to go a little bit deeper into why a particular welder had a defect. And you shoot 2 more of their film or 2 more of their welds. If they pass, then you just go back and fix the one defect, and that piping lot is complete. But if during those 2 sample welds, you find another defect in the same welder's work, you shoot 2 more welds. So now we're up from a single defect going to 2 additional samples. And if one of those have a defect, 2 additional samples. Now, this is where it gets very bad for the fabricator. If this defect leads to another welder, the same welder having a defect in the 2 sample welds, and that same welder has a defect in the other 2, 100% of that welder's welds need to be either x-rayed or cut out and repaired. So it's very important when you choose the lot size in piping to not make it so big. Let's say 500 welds in a lot, and you have 3 welders, each doing 150 or so welds. You can get up to a couple of defects in a welder, and now you're going and shooting 150 welds. So we talk about that in the code. I don't have a slide on that, but you need to choose your lots big enough, yet small enough. And I believe we refer you to a PFI standard. I think it's one of those listed components that that says that this is a good standard to follow, and it gives you some guidance on how to pick a lot. So anyway, progressive sampling is something that's in 31.3. It's not in 31.1. I don't think it's in 31.8. So something that you need to be aware of. And I'll have an example in here of the welds and how progressive sampling could work. All right. Yep, we've already talked about this. The ND personnel cannot examine their own welds. So here we go. So here's an example of steam. It's no superheat in it. There's a visual and a radiography requirement. I'm looking at visual and radiography requirements, and I'm comparing B31.3 to 31.1. And so in 31.3, this steam at 1 megapascal, we could classify as category D. But again, the owner has to say category D. And if the owner says, yes, this is low pressure steam, let's make it category D. Then in B31.3, we have no visual requirement and no radiography requirements on that piping. Except for in 31.1, for this pressure steam, you would have 100% visual requirements, but no radiography. Again, this is low pressure steam. So let's say the steam is 2 megapascals. Now we've upped the pressure. The temperature of steam will go up. And in B31.3, we now have 100% visual requirement that kicks in and 5% radiography. All right. So not all the welds in a steam system, a normal fluid service would be radiographed, but 5%. When you look over at 31.1, when you start getting up to 2 megapascal steam and greater than 175, the visual is still 100%, but the amount of radiography, I have a double asterisk there, and if you read below, it's not a percentage based. The number of RTs is based on whether it's the welds are on the header, whether it's in the branch, depending on what the pipe size is, and the wall thickness. So the 31.1 rules for 2 megapascal steam gets a little complicated. You have to know if it's on the branch, the header, the size of the pipe, and the thickness of the pipe. Where in 31.3, we just say 5%. There's a difference between the two code books. When we get up much higher in temperature, let's see, greater than 400 degrees, would I say it's not percentage based? Oh yeah, this is elevated temperature. This is elevated temperature clause. We have a chapter elevated temperature. Now you're starting to get into the creep range. In the creep range in 31.3, 400 degrees C, I'm sorry, that's a C. So you're talking about 800 F plus. The RT is based on the material construction and creep. And in 31.3, you can see here that we are in the creep range for carbon steel. So the elevated temperature would require 100% radiography, and stainless steel would be 5%. And actually, I think let me hold back on that 100% radiography. I think that's an RT. I'm sorry, that's an MTPT requirement at the creep range. Not that's a very unusual rule. So let's just say that when we get above 400 degrees C, it's based on material construction in 31.3. But in 31.1, it's still based on header, branch, pipe size, and wall thickness. It's not a percentage based. All right, here's some common NDE methods in 31.3. Of course, visual, radiography. Sometimes less common methods, which again, when you're up into the creep range, we are required RT, PT, MT, and UT. Some very uncommon leak testing. Now, when I say leak testing, I'm not talking about the hydrostatic test. I'm talking about helium leak testing, things like that, vacuum testing. Those are very uncommon methods, but there's times like when you're doing a sensitive leak test, you have to do a helium test. It's in the code, but it's not done very often. Same way eddy current testing, acoustic missions. These are things you can use. You qualify in accordance with Section 5, Article 1. But typically, the most common is visual and radiography in 31.3. And then once the piping system is built, now you're getting into UT thickness. And I've used guided wave also to determine pipe wall thickness. All right. Here's an example of how many radiographic shots you would shoot. In this piping set, we have normal fluid service. Question is, how many welds are going to be examined by VT? And the answer is 100%. We have 10 welds in the lot. We have welder number 1 is making 5 welds, and that person makes 3 using GTAW and 2 using GMAW. And then other 2 welders, they come in and they make a weld. And let's see, it doesn't add up there. So let's say that the first welder has 8 welds in the lot, and the other 2 just have 1. So how many welds are examined? And the answer is 3, because for not only is there a 5% radiography requirement, but all welders have to be included in that lot. So 1 shot of welder number 2 has to be radiographed, the 1 weld of welder number 3, and the remaining 8 welds done by number 1. And it doesn't matter which process they use, but welder number 1, 2, and 3 each have to have 1, and you have to have at least that up to 5%. So in this case, out of 10 welds, we shoot 3 welds. As you can see, it's going to end up being 30%, more than the 5%. And go paragraph 341.44B1 for the rules on radiography. Here's an interpretation that came in years ago, and we're all aware of it on the committee. And the question was, in accordance with ASME ANSI B31.1, are these requirements or guidelines on are there requirements or guidelines on minimum distance between welds and a pipe? Minimum distance. You know, how close together can 2 circumferential welds be? Or how close together can a circumferential weld be to, say, a socket weld and a fitting? And the answer is no, we do not provide minimum distances. That's something that, that we have no rules on. And again, we do refer the user to a PFI standard that has some rules on good practice, minimum distance between branches. All right, we have a rule. Now we're going to move on to testing in chapter 6. We have a couple of special provisions for testing, something we added not too long ago. We said drains and vents need not be tested. Here's an example of piping on the discharge of a relief valve that's open to the atmosphere. As you can see, there's 2 or 3, probably 2 butt welds. That 90 is welded to the flange, and then that 90 is welded to a straight piece of pipe. What we said is those 2 welds do not need to be tested. However, it does not say that they don't have to be radiographed. So these 2 welds would still be in the B31.3 system, would have to be considered for random examination, but they don't have to be leak tested. Another provision in section 6 is closure welds. They don't need to be tested. I had an example myself where we were installing a waste heat boiler where we had a steam drum up above. We had piping connecting this waste heat boiler and the steam drum. We had some downcomers that were flanged in, and then we had and then we had these, I guess the risers were the ones right here. And then you had this circulating pipe here that was welded in the field. We made up some spool pieces, the fabricator did, and they decided to make the final welds along here in the field. And so there's a provision in section 6, chapter 6, for a special provision for testing. And it said closure welds need not be tested, but they do have other requirements, such as 100% RT and 100% VT. There's rules in the 31.3 ASME book that says how to handle these closure welds. There's other reasons why you might not need to test. So anyway, we do have a provision to omit testing of a closure weld. And here's an example of a hydrostatic test, and I'm comparing it to 31.1, where 31.3, we test our piping to 1.5 times our design pressure, and then we make this small adjustment based on the test temperature and the operating temperature, this ratio of allowable stresses. If you notice in 31.1, they merely just say 1.5 times design pressure. Here's the example where the 2 codes differ. In 31.3, we also say that this ratio, which is going to be 1 or greater, can't exceed 6.5. And what this does says that, hey, we're going to be hydro testing the pressure, the piping system, maybe at 20 C, but it's going to be running at 150 C. So we want you to stress it in the shop a little bit more so that we simulate how it's going to be stressed out in operation. So that's why we in 31.3, this ratio is also in the boiler pressure vessel code, section 8, but it's not in B31.8, the pipeline code, or in 31.1. Just something unique to 31.3. And I will have an example coming up on how to do that. Also, we allow pneumatic testing. You can see in 31.3, we have a limited range that you can pneumatically test pipe to. Power piping has a wider range. And here's a problem back to our 200-pound steam. That was problem number 1. I want to calculate a hydrostatic test pressure. We're using A53B ERW pipe. If you remember, it had a 1/16 of an inch corrosion allowance. It was threaded. We need to know the stress at test temperature and the stress at operating temperature. So I go look up the stress at, these are the stress tables that are in the back of 31.3. As you can see at 400F, A53 is grade B is stressed, allowable stress is 19.9. At ambient, it's 20 for A53. So what I have to do is pull these numbers forward. I take the ratio of those and I calculate 1.01. So what do I do with this number? I have to multiply it as a correction factor or a multiplier here to the 1.5 times the design pressure. And what that gives me is a slight bump up from not just 300-pound test pressure, but I would have to test this piping system to 303 in order to meet the code. So now the impact and limitations to this ratio, in this case, we have a piping system that's running at 400 degrees. So all I had to do was ratio 20,000 over 19,900. Again, these are in KSI, thousands of pounds per square inch. So we ratio 20 divided by 19.9. But imagine if the design temperature was 950. I would now have to ratio 20 divided by 4, which comes out 5. That means if our operating temperature, or I'm sorry, our design temperature was 950, I would have to take that 1.5 times my design pressure of, say, 200, which gave me 300-pound test pressure. I would now have to multiply a ratio of 5. I would be testing that piping system to 1,500 PSIG if this value here was 950 F. So that shows you how much that this can really bump up your test pressure. But again, if you remember, we limit the ratio to 6.5. So if you happen to be running at 1,100 F and that ratio is 20 divided by 1, we say, no, don't use a ratio of 20. I'm going to back up here a little bit. We say use a maximum ratio of 6.5. That's the maximum ratio you would apply there. All right, so moving forward, that's just an example of how you use this allowable stress table to determine your hydrostatic test pressure. And as you can see, after you get past a few hundred degrees, it starts dropping off pretty fast here in the creep range. This is that elevated temperature range where you start also as an examiner, MT and PT requirements start kicking in. And as you can see, the hydro test requirements start going way up. This is not a good pipe to be used for high temperature, but like I said, it's not prohibitive. You can actually use it to 1,100 degrees. But I can tell you back here, we also give you some warnings back here about using it at elevated temperature. These notes 57 and 59. All right, moving forward. Here's some common rules now. I've used some examples of how B31.3 and 31.1 differ. Here's some common rules between the two piping codes. The hold time. We both say let's hold it for 10 minutes before you examine the piping. For instance, the pressure vessel code, section 8, says once you bring it up to pressure, you can start looking for leaks. But in the piping code, we say you have to hold it for 10 minutes, give it a little soak time before you start your examinations. Once again, that's done. That's an examination done by the fabricator. It's not required to be done as an inspection by the owner. Another thing common between the two codes is when you bring it up to pressure, you can reduce it down to 1.0, your design pressure, before you go in and examine it. And that's a safety thing. About 10 years ago, we got a letter from the safety board here in United States that had a fatality over in the Middle East when they were doing a hydro test pressure. It was a very large pipe. They filled it up with water, but what they didn't realize was they didn't have a vent at the very top. So as they filled it up with water, what they were doing was compressing the air inside to the very top of the piping system, and it was causing a pneumatic test, a hydropneumatic test. And when the inspector went in at 1.5, it was under pressure, the piping system failed. Again, this was done by a company out in Asia. We got the letter and asked us to consider how do we improve the safety of the code because of a couple of fatalities by examiners back about 10 or 15 years ago. So here at ASME, we decided both in 31.1 and 31.3 is after you hold the test pressure to 10 minutes at, in our example, was 303 pounds, you're allowed to take it down to 200 pounds. If you remember this, you're allowed to take it now down to the design pressure of 200 pounds, and the examiner will go in at that point and do their examinations. So that's a safety rule that we both have in 31.1 and 3, and that's there to protect the examiner from past experience. Now, pneumatic tests, automatically we will reduce to 1.0 because we understand that there's there's always energy associated with pneumatic. And also both codes say when you're doing a pneumatic test that you need to pressurize the system gradually. Just don't take it right up to pressure. That you need to pressurize the system gradually, and we provide rules on how to do that. All right, I'm getting down to maybe the last 10 or 15 slides here. So pneumatic test is something that a lot of owners and a lot of users always are worried about doing. Pneumatic test is stored energy versus it's a compressible fluid. So when anything would happen to rupture, all that compressed energy is released. Examiners, you well know that. So we do have a reference in ASME B31.3 to PCC2 that talks about how to calculate this stored energy. How much stored energy are we talking about? How dangerous is the stored energy? So PCC2 provides an energy equation here. And when you calculate this energy, this is the calculation if you're using air. You need to know a couple things about the pressure, the test pressure. You need to know the volume of the system. And you need to know the atmospheric pressure. So you ratio these. So it's an equation that's been derived, and you come up with how much stored energy is in your piping system or your vessel when you're doing a pneumatic test. From there, if you want to calculate kilograms, you divide it by this number here, and it will tell you how many kilograms of explosive TNT is equal to this amount of compressed energy. So with this information, you can now add it to this equation, and it will tell you at different distances what to expect. So if you use a scaling factor of 20 in there, it says put 20 in here, and if you calculate this energy, you multiply it by 2, take the cube root, it says that you can expect glass windows to break. Again, it will depend on how much energy you have here. So this is giving you an idea of when you might expect damage all the way up to fatality. Now in a piping system, unlike a vessel where you can calculate a volume, PCC2 also tells you that you don't have to calculate the entire volume of a piping system, that you only have to go back a certain distance from where an area of concern, And you can see here that distance D, if you're using the TNT model, says go back 11 meters. So any 11 meters on either side, this is how much energy would be there. Of course, as the piping goes on at length and length and length, this is a moving number, but it's so you don't calculate the entire volume in the entire piping system, only a certain amount of volume. And if you don't want to use, or if you want to use the short method, it says, hey, if you calculate 0 to 3 kilograms of TNT, stay back 50 meters. You can see 3 to 5. So this table doesn't work too well if you have, often you might calculate, half a pound or half a kilogram of TNT. It doesn't get down to those small levels. This is what it says. Actually, this table says this is how far something can actually fly. So if you have something with 3 kilograms of TNT in it, equivalent, it says that if it ruptured, something can fly 50 meters into the air. So it gives you an idea of how to establish what's called a safe zone. Okay, I only have a couple slides left. I want to go to part 3. No need to take a break yet. We'll be done in 5 or 10 minutes. So code changes past and future. So some recent changes we've made is in 2018, we used to only do, for normal fluid service, we only used to have the examiner to do 5% of welds. And now we've changed that to 100% of all completed welds shall be visually examined. So that was a change. In 2016, for those that remember the 20% rule for category M, the radiography, we changed that in 2016 from 20% to 100%. So that's a lot more radiography. If the owner decides that it's a toxic material, then the code says you should 100% X-ray all welds. And another thing, and this came in more, say, not as a code change, but interpretation. Somebody asked the question, can you have more than one closure weld in a piping system? And we said yes. So a closure weld initially we thought was going to be used for one final weld to close up a piping system. But as we looked at it and realized if the fabricator wants to go through all the in-process examination requirements, which is to document fit up, your root pass needs to be examined, your filler passes, at the end 100% X-ray it. If you want to go through those 7 steps to do a closure weld, then yes, we issued an interpretation that said a piping system can have more than one closure weld. Future changes, I think this is actually my last slide. We are looking at the code right now prohibits testing using a flammable fluid with a flash point of above 120 F. That's basically the flash point of kerosene, diesel. Right now, the intent is not to use like gasoline or anything with a high flash point, but we're looking at changing that by adding some precautions to it, because many systems, when we get in rural areas, they don't have water, but one thing they do have is the process fluid. So where water is limited in the Middle East, where water freezes in cold climates, we're looking at allowing them to use a more highly flammable fluid with some precautions. We're working on that. So also what the code doesn't address is pressure decay testing. That comes up often with buried pipe or jacketed pipe. For buried pipe, you have to visually inspect all welds, but typically a fabricator likes to dig, weld, and bury, and keep digging, keep welding, keep burying, and at the end, do a hydro test and look for wet spots in the ground. The code does not permit that. The code would require you to visually inspect all buried pipe before you cover it up in dirt. But we're looking at doing adding something to the code to allow a fabricator to watch a gauge over a period of time. And if the pressure holds, then the conclusion is all welds are good. but if the pressure starts dropping and realize one of their buried welds is bad. So part of the language we're looking at adding is you better make some good marks on top of the soil where your welds are, because once you've buried them and you suspect you have a leak, it's going to be maybe hard to go find your leaking weld. So we're looking at language. We've sent that through a couple of ballots. They've come back twice with negatives, which required us to address concerns just like that. How do you identify a leaky weld that's buried? Do you go back and redig everything up? So look for language for pressure decay testing. Also, a change that we're looking at is hydro test gauges. We had an interpretation come in 10 years ago. The fabricator was using a 5,000 PSIG gauge to do a 150-pound test. And the owner or somebody questioned that. And the committee issued an interpretation that says we do not have any restrictions on pressure ranges on test. It reads 150 on the gauge, even though it's barely onto the gauge. And so we leave that up to the owner at this time to control the range of the pressure gauge for the test. But we're looking at adding restrictions to that so that you can't use a 150-pound or a 5,000-pound range gauge to do a small 150-pound test. All right, these are future changes that are in the test part that looked for that to come out maybe even in the 2022 edition. Let's see. Here's I should probably have this up there when we did the example where we had the 3 welders. And even though that the code says to do 5%, if you, it's 5% of the lot with every welder. If you can see what I highlighted, the welds to be examined in each designated lot shall include the work produced or the work product of each welder or welder operator. So if you have a lot of 10 welds, and if you put 10 welders on that job, each doing 1 weld, then every weld in that lot would be radiographed, which is 100%. So if you have only 1 welder in that lot, then you would do 1 of that person's welds, which would be 10%. So as you can do the math, an ideal number in a lot might be 20, because you only have to shoot 1 weld out of 20 to meet the individual radiograph requirements. Once you go to 21 welds in a lot, you're going to be guaranteeing at least 2 welds would be shot. So we don't have rules on establishing lots. We ask that you choose them smartly. A lot of times a fabricator will choose them based on how many welds are on an isometric drawing, or maybe a package of isometric drawings, or maybe all the welds on a skid would be the lot. But again, when you do your 5% circumferential butt radiograph requirement, I wanted to point out here that it's not just 5%, it could be much more, because every welder in that lot must have at least 1 RT shot. All right, I'll end it here by reminding you that we do have an international committee. If you open up your 31.3 book, you will see the B31.3 International Review Group. That review group, I'm always calling into it along with Matt DeLong, the international chairman. The purpose there is to get more international presence into B31.3. We'll have 3 technical meetings a year. That's when the actual whole committee will meet in January, April, and September. So you'll at times you'll be able to call in, listen to the main committee of about 100 people in the meeting. Of course, and then 3 workshops a year that we do off to the side, just the international people, so that we help you become a better code member. And there's Matt's email address. So with that is at the end, and I'll take any questions.
Thank you very much, Chip. Excellent presentation. I have here a couple of questions, good ones. And the first one is to check the schedule. Can we use the ASME B31.1 standard?
Yes. B3610, if you go to table 326.1, you will find that as a listed component. So anything in B3610, which is carbon steel, and B3619, which is stainless steel, are both listed standards. So you can use those as is. But once again, when you do your calculations, unless you know the pipe, like you have to take into consideration the mill under tolerance. But those two standards, 3610 and 3619, are pre-approved. Use those schedules as is. But again, you always have the mill under tolerance if you're doing the calculation.
Okay, I have one which is a large one. Some time ago, a customer wanted the longitudinal weld of the pipe to be aligned with the interconnected one with another pipe when making a circumferential weld, for a cross-shaped weld. I looked for the theme in the B codes, and the only points I found were in the ASME 8 Division 1 UW9 we have, except when the longitudinal joints are radiographed 4 inches, 100 millimeters, each side of each circumferential weld intersectional vessels made up of 2 or more courses shall have the centers of the welded longitudinal joints of adjacent courses staggered or separated by a distance of at least 5 times the thickness of the seeker plate. And I mean, he's adding another information. And at AWS D1.1 2010 5.22.3.1 girth weld alignment tubular, we have longitudinal weld seams of adjoining sections shall be staggered a minimum of 90 degrees unless closer spacing is agreed upon by the owner and fabricator. And the question, is there any point to check in books B? This is the question. And the second question, is this type of case likely to be verified by the committee?
Okay. So to answer it, so it's in section 8, they require that the long welds be staggered. In 31.3, much of the, especially for the manufactured pipe, we don't have that requirement because you often can't find the longitudinal weld in ERW pipe. So those requirements that you cited, which is 2T and all that, that is a requirement of the pressure vessel. It's not a requirement of the piping code for listed components. Now, if you happen to fabricate a pipe, I think the code is silent on that. We don't have rules that I know of that would require you to offset those. So piping has inherently not as much energy in it as pressure vessels. So to answer the question, no, I don't know of any requirement in 31.3 to offset those welds.
Okay, a third one. According to ASME B31.1.3, whenever the hydrostatic test is not carried out, weld inspections must have an image record.
So that's the question?
Yes, that's the question.
So when hydrostatic test is not carried out?
Yes, weld inspections must have an image record.
Okay, so it goes back to the interpretation that I had on maybe slide 10, where I said a question that we might get into the committee: can the hydrostatic test pressure or the test be waived if the owner waives it? And we would answer no. If you don't do a test, then it does not meet 31.3. Now, the one case that you can get out of the test is this came in one time in interpretation on closure welds, and the fabricator wanted to have all the welds in the piping system. Now, it wasn't a big piping system, but it might have been 10 welds. They wanted to know if all 10 welds could be closure welds, and then therefore all 10 welds radiographed and not hydrostatically tested. And we said, yes, all 10 welds could be closure welds. Now, as far as the film, we don't have requirements on what the film is. That's all done under section 5. All we say in 31.3 is if all 10 welds are closure welds, then you can radiograph them all and not do a hydro test. But other than that, you must do the hydro test or some kind of pressure test.
Okay, I have another one here. When do you feel that a pipe system is not required the formal stress analysis?
Yeah, okay. So the B31.3 does not have does not tell you now for category M, we do require a formal stress analysis, which is, you know, using Caesar or pipe stress, one of these. Category M for high cyclic, but other than that, it's up to the designer, that pipe stress engineer, to determine whether or not a simplified approach should be used or a more rigorous. So other than a couple of situations, as I mentioned, category M, high cyclic, where it requires you to do a complicated, rigorous stress analysis, we do not tell. It's up to the designer, because the designer, it's their responsibility. They should be experienced. If you remember, the requirement on the designer is they have to have upwards maybe of 15 years experience if they have no formal university training, or they have to be a professional engineer. So that's not a requirement of when do you do it and when you don't. That's a judgment by the designer, except for category M or high cyclic.
Okay, another one. How to decide whether reinforcement is required for a piping branch connection or not?
Okay, and let me see here if I can get to that. We'll go back to that slide where, there we go. Again, this is one right here where there's no reinforcement. So the question, say that again, a branch connection?
I'm sorry, because we can't see your screen. Let me, Eleni, could you please let me...
Pede para ele compartilhar novamente.
Could you share your screen again, please, Chip? Yeah, we can see it. Let me repeat the question. How to decide whether reinforcement is required for a piping branch connection or not?
Okay, so here's an example. So all nozzles, all branch connections need to be reinforced, but how do you reinforce them is a calculation. If so again, when you put this branch in here, you have to cut the opening of the branch, you put the pipe in, and you have this figure that says, hey, here's my pipe wall thickness, I have to have so much for corrosion, for mill tolerance, for pressure stress, and this really big heavy dash mark is extra metal in the run pipe. This is extra metal. You do the same in the branch, and this distance times this, add these up. There's 4 of them. 1, 2, 3, 4. That has to be greater than this hash mark here. That is a designer's calculation that's done. I do it all the time using Excel or sometimes a hand. If this area here is this area, which is maybe a 1/2 inch times 5 inches, whatever your pipe is, whatever your wall is greater than this heavy, you need to throw a repad in here. Now, if you don't want to do the calculation back here, if you don't want to do the calculation, in this case they did, you can always put an OLET in there, and an OLET is self-reinforced, or you can put a B1611 coupling in there, and those are self-reinforced. Otherwise, you've got to go through this calculation here.
Okay, thank you. Another one, it's how many types of fluid services are available for process piping?
Well, let's see, we have, again, so everything, you have the normal fluid service. You have the category M, which is your toxic. You have a high purity fluid service, and you have a high pressure and a category D. So if you look in the scope, we would have 4: normal, category D, category M, and high purity.
Okay, the last one. What are the disturbing parameters against which the piping system must be designed?
Say that again.
What are the disturbing parameters against which the piping system must be designed?
So what I'm hearing there, the disturbing parameters. So what are some of the key parameters that you look at when you design a piping system? All right, and fluid service would be one of them. You would not want to, that's where you pick your code of construction. That's a key parameter. So some of the key parameters, again, goes back to your formula when you're sizing pipe, which has to do with your pressure is a very key parameter, your fluid service, and your temperature, which drives this S value. Also, the type of whether you're using welded pipe or seamless pipe. Another thing, as you can see here, that dries up your wall thickness is how much corrosion allowance you put on. This right here and threading, as you can see, is most of the reason why you use a Schedule 80 pipe in this application. It's not due to pressure. So a very key parameter is I see piping is sometimes overspecified for corrosion, and they're overspecified for temperature. So choose a good rule of thumb that I use is maybe your operating temperature plus maybe another 10 or 15 C. And corrosion allowance, once again, as you can see here, 40% of your wall thickness is due to your corrosion allowance. So when you use a pipe spec, pay attention to your corrosion allowance to just make sure that you're not using too thick a pipe. So that's the best I can answer that as far as key parameters on designing a piping system.
All right. We finished the morning. Chief,
Great.
I'd like to thank you very much for the presentation, for the excellent presentation. And I'd like to introduce our presenter this afternoon. It's Mr. Paul Davis, Director, Quality Systems, Aftermarket and Construction Services, Wood Group. Mr. Davis have over 40 years experience in manufacturing, project, and commercial quality management, including 25 years of service with Wood Group. A graduate of Duquesne University in Pittsburgh, Mr. Davis' qualifications includes AWS CWE 04061671, Level 2 VT, PT, LT, Vacuum Box, ISO, Internal Auditor, PMI Equipment Operator, and has comprehensive knowledge of ASME, ASTM, and AWS ANSI codes. Mr. Davis is voting member of ASME B31.1 committee, vice chair FNE and E secretary of SGONM, and chair of SGQC. Mr. Paul, welcome. You have the word.
Thank you very much, Antonio. I certainly appreciate that introduction, and I certainly appreciate the opportunity to provide an overview with ASME B31.1. We're going to basically follow the 2020 edition for the overview. And just so everyone is aware, this is ASME's policy that the views expressed in this presentation are not those of the presenter and theirs alone, and may not necessarily be the views of the society in accordance with American Society of Mechanical Engineers policy P14.6. So just wanted to state the disclaimer. So what I'd like to discuss today is pretty much, this is a very high level breakdown. We're really going to talk about the 31.1 code, its general requirements, and in tandem with that, we'll be working with 31.1 best practices. And I've sort of combined those two because you have many, many options of piping codes that people can choose from. But for the power generation industry, B31.1 is widely used for that practice. And then I also want to get into some of the code changes that have just occurred from the past editions. And then hopefully at the end, as everyone has questions, we can have a little Q&A session at the end of this presentation. So with that, if everybody's ready and seat belted in, we'll go ahead and start. And I thought that I would begin with a little background as to what were the drivers to bring about this code. And I think, as most of you, whether are familiar with any type of history, whether it's globally or in the United States, is once we invented the steam engine, which we have to thank Mr. Heron Alexandria, the Greek that did invent the Eolipau back at 10 AD, we've been dealing with steam and steam engines for close to 200 years. And part of the problem was that if everything didn't work right, or if the water levels went down, or the valves would lock up, you would have major problems. So because there were so many explosions, whether it be marine or land from 1820 to 1910, we really needed to create a boiler safety code. So what started this was essentially the boiler, but everyone knows that within a boiler, you have transfer piping, interconnecting piping, balance of plant piping. And so they run hand in hand. And I'm going to just elevate two of one of the major catastrophic boiler explosions that really helped drive the need for a safety code. And the first one was the 1865 Sultana steamboat in the USA, and then the 1905 Grover Shoe Factory. And both of these catastrophic incidents catapulted the need for a technical society to develop a safety code and standards. So the first ASME power boiler code was actually published in 1915. It was the 1914 edition. And from that stem many technical papers. I don't know how that happened. That were written in 1922, detailing various piping designs. And then finally, 3 years later, with the favorable vote of the ASME standards, we were invited to develop a standard for the various types of pressure piping. So as you can see, it took 8 long years and many, many, many committee meetings, and finally they had a draft, was prepared and issued. And ultimately, in July of 1935, about 85 years ago, we now have a code for pressure piping. And as you can see, it was 10 years after the development committees began discussion. So the wheels do not run that quickly through code development, but the necessity, as you can see, has been there for quite a while. And so, as I stated, the first was horrible event was in April 27th, 1865. And this was the worst maritime disaster in the United States. Although this steamboat was designed to hold 376 people, at the time, this was right at the end of the Civil War, they overloaded this steamboat with 2,000 Union soldiers. And shortly leaving Memphis, Tennessee, the boilers exploded, and between 1,500 and 1,800 were dead, depending on the sources that were cited. So that created quite a stir throughout the United States. And before and after this incident, there were many other steamboat and boiler explosions that caused multiple casualties, property damage, and deaths. Another instance that we'll call a catalyst event was a boiler that was in operation at a shoe factory. And in the morning of 1905 in Brockton, Massachusetts, this boiler that was rated for 90 PSI, operating at 80, so it doesn't have to be an ultra high pressure unit, exploded. And that explosion killed 59 people and injured over 150. As you can see by the two photographs, the factory before was a nice 4-story building, and after the explosion, there was nothing left. So the impact of these explosions, and the severity of the explosions really pushed the technical societies to develop safety codes. And that, as I showed you in the previous slide, was what started the ASME boiler code and subsequently the piping codes. But just, for everyone's knowledge, you have various B31 codes. So they're not all the same. 31.1, which is going to be the topic of our discussion, covers requirements of, boiler external piping, which is part of the boiler, whereas ASME B31.3 does not. That is process piping. And although you'll find out later in this presentation that the owner can select various 31 codes, you would normally select the piping code that's, closer to the conditions of which you're trying to design to. So when you're designing a power plant, the majority of the piping in the power plant will probably be designed to 31.1. And another point here is, although some of the 31.1 fittings can be used as part of boiler external piping design, 31.3 fittings cannot. So you have to stay within the confines of the code that you are using, including the materials. Just to give a slight overview of the various piping standards, basically you will see that you normally have a division between pipelines and piping. So 31.4, 8, and 11, which you can see here, cover pipelines, which is transmissions of the internal product, whereas 31.1, 3, 5, and 9 are specific to the service piping. Now, where you have a combination is a newer 31 code, which is B31.12. As you can see, it's hydrogen piping and pipelines. So sort of broke the mold on 31.12, but the normal practice is to separate piping from pipelines. So when you look at the piping codes, whether it's 31.1, 3, or 5, etc., each code does provide for a set of requirements to obtain a safe, reliable, and economical installation. And this is where the term best practices would come into play. This code has been developed over the last 85, 90 years to make sure that as it is amended and upgraded, that new technologies, new information, get added to the code to make sure that we are current. This code was not developed as a one and done book. It basically is a living, breathing document that is updated periodically through meetings and interpretations and additions to the code. But a big caveat here is that the designer is cautioned that this code is not a handbook. It does not eliminate the need for designers or for competent engineering judgment. So although it will provide some good practices and some best practices, it doesn't alleviate the designer from good judgment and competent judgment. In addition to even the 31.1 piping codes, you'll note that there are also additional piping standards found within other codes. One of these is the bioprocessing equipment, which is essentially used for the pharmaceutical processing industry. But there is a reference to this code in 31.3. Basically, people can become certified. You can get a certification, in your quality management system for the specific type of piping and equipment. Another one is the pressure vessels for human occupancy. Now, why do we have all these different ones? Well, again, look at what the piping is being used for or the equipment. Here, you're basically designing this for human life. So it has slightly different criteria than maybe a steam system or a process piping system. And then the same with the boiler pressure vessel code section 3 for nuclear power. Well, nuclear power is different than conventional power, so it may have different criteria and rules that are specific to that industry. And just to keep on with that vein, you can also have the NFPA, which is the National Fire Protection 13 and 24 and 50, which can do sprinklers and private mains and oxygen systems, as well as NFPA 54, which is the National Fuel Gas Code. And many of these are referenced in our code as well. As you have CGA handling of anhydrous ammonia and so on and so forth. So depending on your system and the specifics in the application, you may have to reference various other codes for information. But again, this is specifically going to be about B31. So the B31 rules that we have developed in this code are typically found in electric power generation stations, institutional plants, geothermal heating systems, and the last is central and district heating and cooling systems. And this is found in paragraph 100.1 of the code. If you wanted to look back and make a note as to where to find this, these topic here. Essentially, 31.1 scope is for power piping systems that include but are not limited to steam, water, oil, and gas. And these are the basic systems that one would find in a power generation plant. No, the 31.1 does give a list of various piping that one would find in a steam generation plant or a boiler. And many of you would be familiar with this. The main one being boiler external piping, which is pretty much the jurisdictional point of the piping after the boiler, but before the required valves, blow-offs and blow-down, instrument controls, samples, spray type to superheaters within the boiler and outside of the boiler, pressure relief, flammable piping, whether it's combustible gases or toxic fluids, corrosive fluids. You can have, it even discusses temporary piping, steam trap, pump, suction and discharge, as well as district distribution systems. So as you can see, there's a wide variety of piping that is covered under B31.1. But generally, power piping code, and as I stated, we will use the 2020 edition. It is an international code. It can be adopted internationally. It is used in Canada and Mexico, Europe, in Asia. So it's used all over the world. And currently this code is scheduled for publication every 2 years, similar to all the ASME codes now. There are no longer any addenda. They just redo the code every 2 years. So our next edition, which will be published, will be in 2022. Pretty much a summary of what is contained in this code. Pretty much starts off with a foreword and the committee rosters, intros, and summary of changes, which we'll go into a little bit more detail, and 7 main chapters. As you can see, it's all Roman numerals. Chapter 1 is scope and definitions. 2 speaks of design. 3 is materials. 4 denotes specific references, specifications, codes, and standards. 5 discusses fabrication, assembly, and erection. 6 is inspection, examination, and testing. And 7 is a newer section that has just been brought in the last 20 years, which is about post-construction, which talks about operation and maintenance. And that section was brought into the code to really address condition assessment of piping systems in older power plants. And the biggest problem that our code, we have discovered as people using this code, is that for a lot of the balance of plant piping, which we call CPS, controlled piping systems, which is still high pressure, high temperature, there wasn't a lot of documentation regarding the piping, either from fabrication, whether it's raw material, fabrications, what type of NDE, post-flow heat treats. And so if there was ever a problem and or a failure, it was very difficult to try and trace back to a root cause analysis. So that is why we have chapter 7, operation and maintenance. And that is part of our charter as well, that we pretty much take the piping from its inception at design all the way through operations and maintenance. The last part of our book is mandatory appendices, non-mandatory appendices, figures, tables, and forms, which are easy to find and reference throughout the code. Pretty much, if you ever want to know what the book is about, always kind of go to the foreword, because this will tell you what's the driving factors for this code. And as you can see, the general philosophy underlying this power piping code is to parallel those provisions of Section 1 power boilers, of which this piping is found. The emphasis is going to be on safety and sound engineering practices. And the key part of our 31 code is that it's more conservative than some other piping codes, and it's designed to be that way. But it's designed to be that way to reflect the need for long service life and maximum reliability. So it is always better, even in life, sometimes to err on the side of conservatism, but because of the ramifications of safety and that some of the failures can be catastrophic, we definitely would rather be more conservative than more liberal in the design. But after I state that, the code serves to warn a designer, fabricator, or erector against possible pitfalls. However, as I stated earlier, this code is not a handbook. It cannot substitute for education, experience, and sound engineering judgment. And that, if there's anything that you want to take away from this presentation, that is pretty much it. So even though we're very proud of our book, it is a wonderful source of information and knowledge. Please understand that it's not a cookbook, okay? And it's not a handbook. It provides guidance, and it helps you maybe minimize mistakes that you might make, but it's not a substitute. And the last item here is power piping committees strive to keep abreast of current technological improvements in new materials, fabrication practices, testing techniques, and other endeavors to keep this code updated to permit the use of available new developments. As I stated earlier, this code is constantly changing and updating as new materials and technologies are discovered. You cannot really call this a stagnant code. To get a little understanding of how B31 committees operate, I thought I'd put a slide together to give you a little bit of the hierarchy of the committees. And at the top here for 31.1 is the Standards Committee, which has its personnel and its officers. And directly below that is the 31.1 Power Piping Section Committee, which I'm a member of. And currently there's about 36 voting members and 4 contributing members. And some of the contributing members have been past voting members that have subsequently retired but still wish to add their knowledge and expertise, to the committee. And then underneath that, you basically have all the various subgroups, which parallel, the sections and the chapters of this code, which would be design, fab and exam, general requirements, which if you can't put the item in any of the other categories, it falls over into general requirements because maybe it affects the entire book. You have a subgroup on materials, and then as I stated earlier, chapter 7 is operations maintenance. And then a newer one is the subgroup on quality control, and I'll expand on that a little bit more. And you also have technical committees, F&E, materials, and design. But the subgroup on quality control, again, has been brought about because of chapter 7. And what we're trying to do is we ask for a lot of items to be documented in chapter 7, but nowhere really in the code, the preceding 6 chapters, do we talk about what these requirements are. So what we're trying to do is now put the horse in front of the cart. And we want to say, okay, when you have controlled piping systems, which is pretty much piping that is subjected to volumetric examination. I guess this must be on a timer. It just goes without me. But if you have piping that requires volumetric examination, there are certain criteria that we want the fabricators and the erectors and the designers to maintain and keep, so that 10, 15, 20 years down the line, if there is a catastrophic event, then the paperwork will be there for the welding processes, the heat treatment, the materials, the testing, the design parameters. Everything will be in one nice little package. So that's what we're trying to do here in quality control. It is a work in process. We have an item out right now to pretty much provide for some certification in piping, but without third-party oversight like boiler external piping, but yet have written documentation as to what was done. So that's something that's going through right now, and we can talk about that later if there's any questions regarding that subgroup. Just general information here. Anyone is welcome to come to these meetings. Naturally, now with COVID-19, we're pretty much doing all these meetings virtually and have done that since our last January meeting. But once this hopefully is taken care of, then visitors are welcome, and you can come to any meeting and contribute. You may have an item or of concern or something that specifically is in your business that you're trying to find out, and nowhere better to go to where all the subject matter experts are, whether they'll be design, MDE, fabrication, general requirements. So this is where you'll go to meet those people. The meetings are held 3 times a year. Usually they are January, May, and September, although situations may move them one a month before or after, but that is usually typically when they meet. And then the September meeting is usually a joint meeting with all the 31.1 codes. So, if you want to, if you can only go to one, that may be the one to go to, especially if you have process piping or ammonia piping or hydrogen piping, and you want to meet the various members of all these codes. The September meeting is normally when they attend. And I thought I would just denote our charter here. WIS has been updated recently. There was some discussions about our charter not specifically allowing for post construction activities, which is that chapter 7. So we wanted to make it extremely clear as to what our charter is. So you will now find this charter on our webpage, which simply states is B31.1 Power Piping Committee is responsible for developing and maintaining the requirements for materials, design, fabrication, assembly, erection, examination, inspection, testing, operation, and maintenance of power piping systems. So it's very clear that we do have the authority and ability to discuss post-construction operation and maintenance of piping systems. Basically, in our introduction, we provide a list of all the 31.1 pressure piping codes. They cover pretty much any of the piping that you're going to find in industry, which is power piping, process piping, refrigeration piping, gas transmission, hydrogen, pipeline transmission systems, and building services piping. But it should be clear that in our code, it states it's the owner's responsibility to select the code section that most nearly applies to a proposed piping installation. And that's very important. So, the code itself gives a lot of autonomy and authority to the owner. And this code is under the direction of ASME Committee B31.1, Code for Pressure Piping, which is organized and operates under the procedures of the American Society of Mechanical Engineers, and it has been accredited by the American National Standards Institute. And another caution here is users of this code are cautioned against making use of revisions without assurance that they are acceptable to the proper authorities in the jurisdiction where the piping is to be installed. So again, and we'll talk about this further in this presentation, that you always need to know what is allowed by the jurisdiction and what is the jurisdiction accepted. So especially in the United States, you have to have a good idea of what the states and each of the chief boiler inspectors of the states, what have they accepted? Some have accepted all the codes, some have accepted portions of it, and some have accepted earlier editions of it. So you have to be extremely cautious with just arbitrarily saying, well, we're just going to use the current code because the jurisdiction may not have accepted it. And again, as you read the code, it's not all black and white, many gray areas, and sometimes that's by design. You can have a request for interpretation or suggestions for revision, and you should address these to the Secretary of B31 Committee, 2 Park Avenue, New York. And again, anyone is welcome that is using this code or has a concern or an instance where you need a clarification. That's the methodology to get it done, to get it to the right committee. Some of the key changes that have happened recently in the 2020 edition are we've updated some of the design conditions to align themselves with B31.3. And you'll notice there's been a push in the last few years to get more of a consensus between the 31 codes, whether it's with preheat or post-weld heat treat or design. So there is a push, and it'll continue to go forward, I'm sure, to get these codes more in alignment where they can. You know, there's some have to be different by rule, but sometimes there is no reason to have differences. We have new clarification of visual examination requirements. There's also a new content on the in-process examination in Chapter 6, inspection, examination, testing. And also, as we envelop and develop Chapter 7, we utilize the non-mandatory Appendix 5 to add a lot of guidance and instruction items. And here we've added a new content on damage mechanisms. And you can find this type of information in other sections of ASME, but we wanted to make sure we've incorporated this in our code as well, as it affects various piping systems. Well, I guess we can begin right at the beginning of the book, and I'll try to work through the book in sequence, you know, from the beginning chapters till the end. So, you know, if you have your own book, you can kind of flip along with what I'm doing here. And you can pretty much go word for word with what I'm going on. But essentially, the scope is extremely important so that you know what this code is for. And essentially, it's going to provide and prescribe requirements for design, materials, fab and erection, examining, testing, and inspection. And as I stated in Chapter 7, operation and maintenance of piping systems. And it says where such service requirements necessitate measures beyond that required by this code, such measures shall be specified by the engineering design. In Chapter 4 does contain multiple reference specifications, codes, and standards, which may be sprinkled throughout or referenced in our code. Chapter 1 also really details in the various figures code jurisdictional limits for piping. And these figures are similar to what you'll see in boiler and pressure vessel section 1, but I thought I would pull one example out, and this is pretty much for drum type boilers, which you may be familiar with if you work with section 1 or 31.1. So just before we get to that jurisdiction, pretty much these are the three designations of piping found in the drum type boilers. The first is boiler piping. And this is where the boiler pressure vessel code has complete administrative jurisdiction and technical authority. So you have to go to section 1 for this type of piping. And typically this piping is transfer piping, interconnecting piping, downcomers, and they're known as boiler proper piping. And this piping is normally recorded on a Form P4 form. The next type piping is boiler external piping, which we call BEP. Now here, the ASME Boiler Pressure Vessel Committee has complete administrative jurisdiction, but B31.1 has been assigned technical responsibility. So when you're looking up the requirements for BEP, you've got to basically look in both books, okay? Pretty much this piping is main steam, feed water, vent, blow up, blow down, drains, and that's normally considered boiler external piping up to the applicable valve. And you'll see that, you know, on the code breaks of the jurisdictional limitations. And this piping, boiler external piping, is normally recorded on a Form P4A. And these forms you will find in ASME section 1. And the last type of piping for 31.1 is what we call non-boiler external piping. People call this piping also balance of plant. Now here, B31, the ASME Code Committee for Pressure Piping, has total administrative and technical authority. This is normally considered balance of plant piping and consists of main steam, feed water, cold, hot reheats, vents, drains, after the code break valves. And just so everyone's aware, no third-party oversight, for example, an AI, nor data reports are required for this piping. And a subset of this piping is what we are working on in our subgroup for quality, and we'll get to that a little later in the presentation. So I don't know if any of you are familiar with this type of jurisdictional diagram, but this is a typical one for drum type boilers. It's not indicative of everything that you'll see on a drum type boiler, but it will give you the guidance of where the boiler proper is, which is pretty much all of the boiler equipment, any of the interconnecting piping between this equipment, and any of the transfer piping between one set of equipment to another. So that's all considered the boiler. Then as you get to the takeoffs of this equipment, that begins, as you can see, the boiler proper is just a straight line. The boiler external piping is pretty much starts with a dot and runs through the applicable valves. And so that's the boiler external piping, as we discussed, is going to require third-party oversight with an AI, and will have to be certified on a data report form. And where all these dotted lines are on this chart, that's what we call non-boiler external piping, okay? And usually that'll be after the required valve. Sometimes it's the first valve, and for drains, it's 2 valves. But as you can see by these charts, and there's other types of jurisdictional limits, not just for drum types, but ones throughs and Herzigs and different types of steam generation equipment. But it just gives you an overview and an oversight, if you're ever looking through a P&ID, where the various code breaks should be. And the other thing I wanted to mention too is if you have a book, you can look at in paragraph 100.1.3, list items that are not covered. I mean, every book says what it does cover, but it should also say what it does not. And essentially this code doesn't cover any of the equipment, that are covered by section 1, such as economizers, heaters, or pressure vessels for section 8. It doesn't cover building, heating, and distribution steam and condensate piping designed for 15 PSIG or 100 kPa or less. So those things are not covered by this code. Piping for hydraulic or pneumatic tools. Piping for marine or other installations under federal control. And also, people might not know this, but piping included as part of a shop assembled packaged equipment assembly within a B31 code piping installation. So theoretically, you can have a skid with all this piping and instrumentation and stuff that is not covered by 31.1. And that is true. I mean, sometimes you may have an ammonia system or something like that that is put together on a dilution skid. And the owner may say, well, I want that to be to 31.3 because it in essence is, process piping. So you can have different codes in a power plant. So really, the other thing I wanted to let you know that, this chapter 1 does contain definitions that we use throughout the code. And if there are other sections that contain definitions, then they're specific to that section. But if the definitions that are used in chapter 1 are definitions that are used throughout the main body of the code. And some of the key terms, as we discussed earlier, would be covered piping systems. And again, these are piping systems on which condition assessment activities are to be performed. Welding and heat treatment technology. If you want to know the various types of welding processes, different types of heat treatment, whether it's post-weld, whether it's annealing, whether it's solution annealing, you'll find that terminology there. And even something as simple as the difference between a pipe and a tube. You'd be surprised how many people do not know the difference between a pipe and a tube. Again, the owner is defined because that term is used throughout this code, and it is used to denote responsibility. And even though this is a safety code, it is also a code that develops responsibility. You'll also note the shoulds and shalls as they're used in this code, where the shoulds are pretty much good practice and the shalls are mandatory. If you see the word shall, you must do it. Various types of stresses, because there's a lot, this is a design code. So all the definitions for the various stress stresses that you're going to come across are denoted there. And then also another term that sometimes gets confused is the term inspection, which in our code denotes the activities performed by an AI or an owner's inspector to verify that all required examinations and testing have been completed, versus the word examination, which denotes the procedures for all NDE examinations. So people sometimes use those words interchangeably, but they do have two separate meanings. Chapter 2 is design. Now, this is not my strong suit, ladies and gentlemen. We'll go through it. I am not a designer, so we're going to go through this section so that you can, if that is part of your job description, you'll know where to go, where to look for the various requirements for design. But generally, power piping systems shall be designed for the most severe condition of coincident pressure, temperature, and loading, except as herein stated. So that'll tell you that this code does contain design flexibility, and not everything is black and white. As I stated earlier, good engineering judgment can never be left at the door. You must always keep that with you. Section 101 talks about piping system design conditions that should be considered. And it basically, there could be additional ones, but the main ones are temperature, pressure, ambient influences, dynamic effects such as impact, wind, earthquake, etc. Weight, weight of the piping, weight of the fluids. Even if you're going to do a hydrostatic test, you need to consider the weights that's going to put on the piping. And then thermal expansion and contraction. In section 102, the piping system gives you the design criteria, which will give you some information regarding standard fitting pressure and temperature ratings, which are used throughout all piping systems. A large portion of this book, which are the allowable stresses. This is similar to the other ASME codes. And ours is all these allowable stresses are listed in the mandatory Appendix A, and they should match up, I think, pretty much consistently with those values found in Part D of Section 2. It also shows the stress formulas. It gives you the ability to calculate min wall thicknesses for bending. It gives you a list of longitudinal weld joint equality factors, as well as casting quality factors. So depending on whether it's a pipe or casting, you have different criteria in the design. Part 2 of the design is pretty much contain criteria for the design of piping components. And part of that is referred, you go and reference 102.4.71, which is the weld strength reduction factors, which are very important. Section 104 is min wall thickness calculations. And here you just see what product you have, whether it's straight or curved sections of pipes, branches, miters, flanges, reducers. We even have design criteria for specially designed components and piping analysis, and that's more of a validation. Part 3 gives you the selection and limitations of piping components. And Part 4 is selection and limitation of piping joints. So it's very good information and guidance is found here. Sections 105 to 109 provide some information regarding metallic pipe, non-metallic pipe, fittings, bends, intersections, valves, and pressure relief devices. And continue with the flanges, gaskets, and bolting. But Part 4 lets you discusses the welded joints. And this is where the connections are. So you got the welded joints, flange joints, expanded joints, threaded joints, flared and flareless, compression joints, union, bell end joints, brazed and soldered, sleeve couple, and other proprietary joints. So the code is trying to pretty much cover the majority of the piping that you're going to come into and the way that these piping sections are joined. Part 5 in design continues to expand on expansion, flexibility, and pipe supporting elements. It basically provides the designer with information regarding the designing of a piping system subject to the thermal expansions, contractions, or other displacement stress inducing loads. You can find the coefficient of thermal expansion should be determined from the values given in mandatory Appendix B contained in this code. It also provides for methods for flexibility analysis and design of pipe supports. And again, as I can't state this strongly enough, there's no substitution for sound engineering judgment and practices. That's why we have the following warning that alludes to that. And it basically says right out of the code. Warning, no general proof can be offered that this equation, this is one of the equations, will yield accurate or consistently conservative results. It was developed for ferrous materials and is not applicable to systems used under severe cyclic conditions. So as you read this code, look for these warnings, look for these cautions and things, because it's not a one size fits all. You really have to use your engineering judgment, whether it is applicable. So just keep that in mind for all the designers out there. Part 6 basically talks about specific systems and any specific requirements for the design thereof. So you're going to have separate requirements for piping designated as boiler external piping, which we said earlier was steam, feed water, blow off, drain, etc. You also have specific information for non-boiler external piping, blow off and blow down piping, instrument controls, fitting and joint requirements, special safety provisions, and also for desuperheater piping, specific requirements for desuperheater piping on steam generators, main steam and reheat, pressure relief piping, flammable gas and toxins, and exhaust and pump suction. So each one of these specific piping systems has specific requirements attached to them. Chapter 3 is pretty self-explanatory. It basically contains the limitations and required qualifications for materials based on their inherent properties. So the use of these materials in piping system is also subject to requirements and limitations in other parts of the code. But essentially, if your material is listed here, you know that it's safe to use in a B31 application. And most of the B31 materials, they're all ASTM designations, but if you are using BEP piping, remember that you need to use an SA designation because Section 1 has the administrative authority on that. So basically, what are the highlights of Chapter 2 in the materials? Well, here they're providing limitations on materials, give you the upper and lower limits that you can use, and this is all based on the charts. They also tell you a caution regarding the use of carbon steel above 800 degrees Fahrenheit due to graphitization, using of gray cast, malleable and ductile irons, cladding or lining, and non-ferrous materials such as non-metallic pipe. It also provides information on creep strength enhanced ferritic materials, specifically A217 grade 12A and A1091 grade 91 castings. So they're elevating the specialness of this type of material. And again, there's been a lot of discussions over the last 25 years regarding grade 91 and 92 and various creep strength enhanced ferritics. So they're going to be very specific on your heat treat requirements, weld repair, overheating requirements, and certification. And Chapter 4 is our chapter where we reference our specific codes and standards. And this is right verbatim out of our book. The documents listed in this table may contain references to code standards or specifications not listed in this table. So it may reference a different standard that may not be here, but again, you have to read everything in its entirety. But such unlisted code standards or specifications are to be used only in the context of the listed documents in which they appear. So in other words, where we're trying to make a reference here, we're not possibly adopting the entire book, or we're not looking for the entire reference, but where it's specifically referenced, we're asking you to look there for additional guidance. Where the documents listed here contain design rules that conflict with this code, the design rules of this code shall govern. So pretty much as you go through this, and if you have worked within 31.1, you can flip through, this Chapter 4, and you'll find AISC, ANS, API, ASC, ASME, ASTM, AWS, you can see on and on, American Water, expansion joints, FCI, MSS, NFC, PFI. So all these standards which have an application to piping systems are referenced in our document here, and as they are referenced in our code. So for me, the next two sections here are my meat and potatoes in chapter 5, which is fabrication, assembly, and erection. And here's where you're going to go, you know, once you've got the design finished and it's been locked in, and now you're going to go ahead and fabricate this piping. Like I said, once you do need to know what you have. Are you fabricating boiler external piping? Are you fabricating boiler proper piping, which would be part of section 1 and not in this code? Or are you fabricating non-boiler external piping? So it's important to know the piping you are fabricating. And on the basis of that, you can look at the various sections here for welding. And the welding here will give you all the information that you need regarding the use of electrodes and filler metals, backing rings, the type of welding procedures that you need, weld reinforcement limits specific to this code, welding details. And you can also use standard welding procedures in our code, which have been developed by AWS and adopted by our code. But there's also reference made to ASME section 9 and part C, which is for filler metals and electrodes. So again, the wealth of information is contained here of where your parameters are as you're doing your fabrication. Paragraph 128 is the same as above, except it's for brazing and soldering. Paragraph 129 discusses bending and forming. And here you're going to find where you have specific requirements for hot or cold bending, and are there requirements for post-bend heat treatment based on the forming strains, and design temperature for austenitic/nickel alloys and creep strength and ferritic materials. So that's a good section to get familiar with, especially once you're getting involved in bending and forming, if you have any additional requirements involving post-bend heat treatment. Paragraph 130 discusses piping supports. Paragraph 131 is welding preheats. And this section, so everybody knows, lists mandatory minimums for preheat. And it's found in table 131.4.1-1. Now you should understand that section 1 contains preheat temperatures as well, but they are not mandatory. But in B31.1, these preheat temperatures are. And I don't know how well you can actually see this. If you have your book, you know what this is, but this is the table for preheat temperatures. And as you can see, it goes through the various P numbers, which 1, 3, 4, 5A, 5B, 6. I can't really see this too much, but you got 9B, 10, 15E. But essentially, these are the requirements for preheat. And it'll give you a minimum in both Fahrenheit and Celsius. And there's also some additional notes there that you may see here. And some of it is based on material thickness. Some of it just says all. So if you have that material, you're going to preheat it, whether it's 1/8 of an inch or 8 inches. Another very important topic in this chapter is post-weld heat treatment. And again, all the codes have post-weld heat treat requirements for various materials. But while you're dealing with the piping code, you need to look specifically for the piping code's heat treatment requirements, which may not be the same as section 1, section 4, section 8. So keep that in mind. But the important terms for us now, and this has been something that has been generated in the last 4 to 5 years to gain more consistency of the 31 codes. So we're using this new terminology, and this terminology is important to know. And the most important term right now is controlled thickness, and you'll see that in your post-weld heat treat charts. And theoretically, it's designed as the lesser thickness of the weld or the thicker the materials being joined at the weld, or the thickness of the pressure retaining material if the weld is attaching a non-pressure containing material to a pressure containing material. And that definition is very important as you decide whether or not you are required to perform post-weld heat treatment or not. The other important term here is the thickness of the weld. So for groove welds, it's the thicker the two butting ends after weld prep. For fillet welds, it's the throat thickness of the weld. Now you may have a combination of both. You may have a groove weld with fillet welds, in which case you have to add everything together to determine what your thickness of the weld is. Now in table 132.2-1, you get exemptions to mandatory post-weld heat treatment. So essentially you have to think, well, everything has to be post-weld heat treated, and now I'm going to go look to see what the exemptions are. And sometimes the exemptions are easily met and the item doesn't require it, but you need to you look at the entire chapter regarding post-weld heat treatment to see. So the table itself is broke down by P number, the term control thickness, the type of weld, and that's why it's important to know what type of weld you have and the thickness thereof, and any additional limitations. And there is a common note throughout the code that even though the post-weld heat treat may not be required, a design engineer may still require it to relieve welding stresses, etc. So just because it's not required by the code doesn't mean it may not be good practice to do it. And a design engineer needs to make that call. In paragraph 132.7 discusses post-weld heat treat. It can be performed in a furnace. It can be performed locally, specifically to a given weld. In chapter 6, we have inspection, examination, and testing. As I said earlier, inspection and examination are two separate terms. So you'll see that as we break them down in paragraph 136. 136.1 talks about inspection. And if you're inspecting BEP, that verification is by the authorized inspector because you have third-party oversight for BEP. If you're looking at non-boiler external piping, well, then it's the owner or the owner's designated inspector is responsible for that verification. But regardless of which inspector it is, the rights of the inspectors is provided for in paragraph 136.1.3, which essentially provides for the right of access. You have to allow the inspector access to your facility to, whenever he wants to, and that's verbatim right in our code. Paragraph 136.1.4 lists the qualification requirements of the owner's inspector. So there's certain criteria that if you go to that list and say, hey, I'm going to assign somebody as my inspector, take a look at the requirements there. It's not just you just pick anybody out of the blue, but they have to have the correct background, education, and experience. So in 136.2, we have inspection qualification of an AI for BEP. For those requirements, you have to go to boiler and pressure vessel, section 1, PG 104 to PG 112. And that'll give you the information of what the requirements of the AI are. The other criteria here is the AI must be employed by an ASME accredited authorized inspection agency, which we call an AIA. Paragraph 136.3 discusses examination. And as I stated earlier, examination denotes a function performed by either manufacturer, fabricator, erector, or party authorized by the owner to, then include NDE. So you have your visual, radiography, ultrasonics, eddy current, LP, and magnetic particle methods. So the examination criteria is going to be listed right here. Paragraph 136.3.2 provides requirements for the qualification of NDE personnel. And this will also reference other codes as well, which is section 5 of ASME. But it gives you information on instruction, training, vision acuity, written and performance examination. So it'll tell you exactly what the criteria is for the NDE personnel. But again, it's not just black and white. So they'd also give you some alternatives to those requirements. So again, you need to read through these paragraphs specifically to see what the requirements are for people performing examination to this code.
Oh, I'm sorry for interrupting you.
Yeah.
Would you consider to make a quick break, 10 minutes break?
Oh yeah, right now we can do that. If you would like to do a 10-minute break, let's go 15. Let's all come back at 1:15, or for my time, which will be 15 minutes from now. Okay?
3:15 from here.
Yeah, 3:15 for you, 1:15 for me.
Okay, thank you.
You got it, buddy. Thank you. Of the various charts and tables and figures that I can assist with, then hopefully that'll help. But in the meantime, I'm just going to continue to run through the various sections so that for those that may not be as familiar with this code, where they can find certain information and certain requirements. So I just hope everybody understands that's sort of how I put this together. I didn't know exactly what we were looking for here, but hopefully the post session and discussions will help if there are any concerns. Okay. So I'm going to continue here on chapter 6, which is, as stated, the inspection, examination, and testing chapter. And probably the most important table in this section is table 136.4.1-1, because it's mandatory. And this is where you will find mandatory minimum NDE. And considerations are based on the type of weld and pressure and temperature. So if you're looking to put together the requirements for any specific welds for those pipings that is fabricated under this code, this is a very important table to look to. This table also provides for acceptance criteria for the various types of examinations, whether it's surface or volumetric. And the table pretty much clearly states that for welds other than those that are covered in this table, only visual examination is required. But visual examination is always required in this code. So just because a weld may not be listed here in this table doesn't mean you're not supposed to look at it. And just for information here, specific to B31.1, and there may be other codes that do this, but I know in our code that the non-destructive examination for P numbers 3, 4, 5A, 5B, and 15E material welds shall be performed after post-weld heat treat. And they do give you a little caveat here, unless directed otherwise by engineering design. But most people pretty much know that to perform the post-weld heat treat, the NDE after the post-weld heat treat. But the problem with that is, if you're going to radiograph a weld and you've already done all your visuals and your post-weld heat treats, and you radiograph it and you find out, whoops, didn't pass, I got to do a repair, then you have to post-weld heat treat again. So there is a risk with this requirement. A lot of people, if they're working under this code, may elect to do some type of informal or informational examination before post-weld heat treat. You know, you might want to do UT, you want to scan, or you want to make sure, or you'll do layered MT. You're going to do something to make sure that by the time you post-weld heat treat, that you're not going to find any flaws when you do your examination. As I stated, this is one of the most important tables for this chapter, and it pretty much will give you your requirements. And essentially, in a nutshell, although you have to read all the limitations, for butt welds, whether they be girth or longitudinal, you are going to perform volumetric examination, which in this code is RT or UT, for those piping systems that are over 750 or 400 C and all pressure. So when you have a high temperature piping system, you're going to pretty much perform volumetric examination for all piping over NPS 2 or DIN 50. Now, if it's under the DIN 50 or the NPS 2, then you'll do MT or PT. But the other criteria here is, well, what if you have temperatures between 350 and 750, or 175 C and 400 C? And then you have pressures over. So this is a high pressure operating within a lower temperature zone. Well, for that, you still have to do volumetric examination, but the criteria is expanded a little bit. So you'd have to do it for anything over 2 inches, but here you have a thickness requirement as well. So it also has to be over 3/4 inch or 19 millimeters. So you have to meet both criteria. If you don't, then VT is required for all thicknesses 3/4 and less. And then the last column just says all others, and it's going to say visual. So as you read this table, there's plenty notes that you have to refer to, so you can't just read the table without referring to all the notes below. There's general notes and then there's specific notes. So this whole table, again, you can work it through with various examples, but this is our determinative factor to determine the type of examination required for a specific weld within given design parameters. Also, we have another table here in our code, which gives you a little guidance as to what type of NDE examination will be best for a certain type of imperfection or flaw. So if you're looking for cracks on the surface, well, visual is good for that. So is MAG, PT, radiography, ultrasonics, you can find that. If you have internal cracks, well, visual is not going to help you unless you got Superman eyes. MAG, unless it's really very close to the top surface, because MAG can go slightly subsurface. That's not a good method. But here's where your radiography and ultrasonics are perfect for that. And subsequently, undercut weld reinforcements, porosity inclusion. So as you can see, and it also has the notes, and you have to read the notes as well, because if you don't read the notes, you may misapply what's going on here. So again, with the weld reinforcement, well, visual is good for that, but it says note 1. Well, in our code, that applies only when the outside surface is accessible for examination, and or when the inside surface is readily accessible. So what this is not telling you to do is to go in there with remote visual equipment, like a borescope, and look at the inside of the weld. If it's not readily accessible, you're just looking at the outside of the weld. So keep in mind that the notes are very specific for the application, and you read the notes so you don't think that you need to do something or go over and beyond what the code is requiring us to do. But again, this is for guidance. It's not mandatory there. It just gives you the guidance, which will help you make a selection as which type of examination you may want to use for the type of imperfection you're looking for. Continuing on in chapter 6, paragraph 136.7 discusses pressure test. And pressure test is to be performed following completion of all fabrication activities, post-weld entry, and NDE. So you have to do preparation. How do you prepare for a hydro test? Well, you ensure all the welds that have not been previously tested are exposed. So you can't cover them up with insulation, where you can't really see them. You have to consider additional supports due to the weight of the testing fluid. Perhaps there might be some equipment along this testing piping system that can't see the type of pressure, so you got to restrain them or isolate them. And then you also have to consider the test medium's thermal expansion on your system. So it depends on the type of piping you have here. So if it's boiler external piping, pressure testing shall be in accordance with Boiler and Pressure Vessel Section 1, PG 99. So if you've got boiler external piping, you're looking outside of our code for the requirement. So normally the BEP piping is tested with the boiler. For non-boiler external piping, you get some options here. You can test in accordance with 137.4, which is hydrostatic testing. You have an option for pneumatic at 137.5. 137.6 is mass spectrometer or halide testing. And even 137.7 is initial service testing. So you have many, many options. It is requiring testing, but you have options as to how you can test the systems. And sometimes the easiest one just may be the initial service test. But all the criteria is listed in these specific paragraphs. And now one of the newer additions to the code that we now have is paragraph 1. Whoops, let's go back to where I want to go. Paragraph 137.8. And this is new to the 2020 code. It now allows for an alternate to hydro testing and pneumatic testing using NDE. So again, this is a very specific section. It's not there to try to remove the requirement for testing, but if for some reason testing is just not possible, then it does provide a way, a path forward to now do NDE. And it's very, very restrictive. And so if you know you have to use this paragraph, you need to know that early in your fabrication cycle, because there's a lot of in-process inspections and examinations that have to occur in order to take advantage of this paragraph. And chapter 7, as we discussed earlier, is operation and maintenance. And we added this chapter in 2007. The people that belong to to this subgroup have always believed that the piping code 31.1 has always been assumed to be a new piping code. But B31.1, if you look at the charter for B31.1, it basically talks about operations and maintenance. So we've always felt that we've had the ability to go beyond there. And what this does is we've always had an appendix that talked about the guidance, which is our non-mandatory appendix 5. And we thought, well, okay, this good practices can be found there, but it's not making people do what we feel they need to do to ensure a safe operating piping system once it's been installed and once it's operating. So chapter 7 is basically to provide additional requirements. And basically the overview here, and I'll just read it verbatim, is safety is the overriding concern of operation and maintenance of power piping. Managing safe piping service begins with the initial project concept and continues throughout the service life of the piping system. So after you've hydro tested your piping and you're done, that doesn't mean you just walk away and go, hey, it's good for 30 years. There's certain maintenance requirements and operational requirements that you have to do to make sure that your piping continues to operate safely. So basically this chapter is written not about all piping, but basically CPS piping. And CPS piping is defined in paragraph 100.2 as piping systems on which condition assessments are to be conducted. As a minimum, for electric power generating stations, CPS also includes NPS 4, DIN 100, and larger piping and other systems that have a design temperature greater than 750 F, 400 C, or a design pressure greater than 1025 PSI or 7.1 megapascals. And essentially what that drives you to is piping which is subjected to volumetric examination should be considered CPS. Okay. Initially, we had CPS piping as main steam, non-BEP main steam and hot reheat, cold reheat, which can be that. But it also can be any other system that the owner, feels is necessary to be included for condition assessment activities. So paragraph 139 of this chapter talks about how the operating company shall, and again, this is not a should, it's a shall, issue written operation and maintenance procedures. So instead of, you've got to have a written documentation of how you're going to operate and maintain your piping equipment. Paragraph 140 provides a list of required documentation for CPS. And as I stated earlier, the problem with chapter 7 in a nutshell is the code itself should be asking for this stuff earlier in the code. And that's where the subgroup on quality is coming in And hopefully in the next year or two, you'll see some new additions to the code that talk about the requirement for documenting CPS piping systems from design all the way through test. And that is right now in the works. That's what the subgroup on quality is set up to do. I am the chairman of that subgroup, and we now have one very large item that is going through committee right now that spells out how we think this shall be accomplished. And again, we initially thought perhaps maybe we should have a certification program similar to boiler external piping, but we've basically backed off of that. And now we just want to make sure that we have a certifiable program that's documented by the users, the designers, the fabricators, the assemblers, and the erectors for their specific parts. So we're basically looking for people to take responsibility for their portion of the work. And so I got a little off topic there, but I think it all ties into what's going on in the subgroup for quality. Paragraph 141 requires maintenance of records, including failure analysis. And again, all these requirements are so that in the event that there is a failure or a catastrophic failure where there's loss of life, that you can go back and perform a very valid root cause analysis because the records are there. The biggest problem we had, when they started to think about adding this chapter was the poor people that were trying to do this analysis were finding there's just no information. That people viewed balance of plant piping as an afterthought, and they didn't really care about, and I'm just basically summarizing, but they didn't really care that all the records and that were kept in one place. And so, maybe the A&E had some of the records, but the user didn't. And then after 10 years, 20 years, people retire or gone, you lose that traceability. So hopefully we're going to correct that as we go forward. Continuing chapter 7, paragraph 142 provides for rules for piping and pipe support maintenance. Paragraph 143, requirements for repairs to CPS, which means you can either use the original code edition or a later edition for these repairs. But you have to remember, anytime you're utilizing the code, you need to utilize the code in its entirety. You can't cherry pick because, hey, back then I didn't have to post-load heat treat, now I do, or hey, back then it required examination, now it doesn't. That's not the way you pick your requirements. Whatever code edition you use as allowed by this code needs to be used in its entirety. Paragraph 144 provides information on CPS walkdowns of piping systems and supports. And if you see something, it's like the new adage, if you see something, say something. Evaluation is required. You can't just see something, mark it down, put it in your notepad, and then put it in the drawer. You see something that's wrong, you've got to continue on with the process. And the next step is, why is it that way? Perform an evaluation. Paragraph 145 provides a list of CPS degradation mechanisms. And this now points to paragraph E12 in Appendix 5. Now, Appendix 5 is non-mandatory, but provides great guidance for the mandatory requirements in Chapter 7. Paragraph 146 provides for documentation of dynamic events. Sometimes you may have a very large steam hammer or something that's going on in your system that creates an event. And so you want to make sure you record that or have it in your PI data so that if something ultimately down the line is discovered, you can now figure out, hey, well, I remember when that happened, and perhaps that, is the root cause of this damage. And paragraph 147 does provide for instructions for re-rating piping systems. Currently, it's some instructions for uprating. There is a discussion involving derating, but that is still in the subgroups and may take a little longer to flush out. The balance of the book is, and again, for those of you who are familiar with this, I apologize, but I just want to give you this roadmap. The balance of the sections have the mandatory appendices in there. And some of these, as you saw, were referenced earlier from the design section. You have Appendix A and B. C is moduli of elasticity. So a lot of these are from the design chapters. Appendix F has the reference standards. G is nomenclature. Appendix H, again, if you're looking to submit an inquiry and say, hey, I'm confused. What do you really mean by this paragraph? Then it shows you how to prepare a technical inquiry to the 31.1, and you can request an interpretation, or you can request a change be made. But usually people are asking for interpretations, and this is how you do that. Appendix N gives you rules for non-metallic piping, for those of you that have need for that. Appendix O is a use of alternative ultrasonic acceptance criteria, where it's fracture mechanic based. And remember, now these are all mandatory appendices. So these, these are all the shalls of the appendices. And Appendix B is a metallic bellows expansion joint. So when you're, for any of these appendixes where you're going for information, this is all mandatory appendices in our code. We also have non-mandatory appendices. Again, this isn't good information for those that are involved in design, or looking for a little bit of information on corrosion controls, or even operation and maintenance guidance. So here's where you would go. Appendix 2 is good for rules for the design of a safety valve installation. Appendix 5, corrosion control for 31.1 power piping systems. And here we discuss methods of internal and external corrosion control, and also how you can monitor FAC concerns. Appendix 5 is a very good appendix for recommended practices. And again, this rolls hand in hand with Chapter 7, which is mandatory. Appendix 5 is not mandatory, but it really does, contain a lot of good information. And you will find in this particular appendix, it has its own set of definitions. So even though that the code has in Chapter 1 definitions, these definitions found in Appendix 5 are specific to this appendix. So don't use the definitions here for the balance of the code. Again, the requirements in this section are recommendations. Pretty much the word should is used, but you'll see a few shalls as well. But again, it's non-mandatory, so it's just very good guidance. It does provide a lot of direction and guidance on the how-to. How do you prepare the records? How do you maintain the records? What am I looking for? So this is where I would go to find that information. It also contains a very comprehensive list of failure mechanisms found in various types of piping systems. So it gives you good definitions of creep and thermal fatigue and FAC and graphitization. So, it's a good place to go to look at what type of mechanizations. If you're trying to develop a program, to do your inspections and examinations of your piping system, this has got a lot of good background information for you to do that. Continue on with the non-mandatory appendices. We also have Appendix 7, which is procedures for design of restrained and underground piping. Again, this one also has its own set of definitions, but it's specific to restrained underground piping. So, those, you may not need these definitions in the other areas of the code. And it only relates to those sections of the piping that are buried. So if you have something that's both buried and non-buried, only the buried portion of the piping would be affiliated with Appendix 7. Appendix 8 is guidelines for determining if low temperature service requirements apply. And here it extracts a little bit of B31T, which is for low temperature, and focuses on services that are exempt. It also provides a table for low temperature service requirements and limits by the material group. So pretty much what has really changed currently? Well, a big one was the NDE in lieu of hydro, because prior to this getting inserted into the code and approved, you really didn't have any leeway. So if you were making a closure weld in a piping system, and you couldn't test the piping beyond where the closure seam was, that seam, a lot of times people would go ahead and use volumetric examination, but it really didn't allow that in the code. So now that we have instituted this NDE for if you have that closure weld, you can now, there is a pathway to do that. Another change is B31P, which is now a consensus preheat and heat treatment across the 31 codes. Because I always found it very strange, and so many those online here, that if you go to 31.1 or 31.3 or whatever different code, or even section 1, you know, because it also has boiler proper piping in it, that there were different requirements for preheat and post-weld heat treat, and yet the materials are the same. So if you have a P5A material in the boiler for a transfer piping, and then you had some P5A and boiler external piping, why after you fabricated them are these requirements so different? And you needed, and that's why you need to know, you know, in your piping ISOs, am I in the boiler proper because it has different criteria for NDE and heat treatment, or am I outside of the boiler proper and I'm now into the BEP, you know, and now I'm into the non-boiler external? So you need to know where you are across the piping sections. So that's extremely important as well. And then the last thing, as I spoke of previously, was this QC definitive program for CPS, controlled piping systems, as a subset of NDEP. So this program is not going to be for BEP because boiler external piping is already covered by section 1 and requires a P4 form and an AI. It does have third-party oversight. This program here is not going to have third-party oversight, but it's going to be very, very definitive as far as how it's documented and the information that is to be kept and how long this information is to be kept. So again, this QC program that we're going to add to our code is basically to add value to those requirements and provide a pathway to those requirements in chapter 7. So this, like I said, hopefully we're going to shoot for the 2022 edition to get this in there, but please know that it is coming. So just so you understand how the changes of each section are shown in our code, if you really look at the way the pages are put together, you'll see that the changes are organized by page, location, and description. So if you look at the summary of changes, it'll give you all that information. And if you're actually in the body of the code itself, you'll see a little parenthesis. So in this particular instance, paragraph 100 was updated or revised in the 2020 edition. So as you go through the 2020 edition of this code, if you see that little notation of a 20, that'll tell you that there has been a change there and it is different from the 2018 code. Some of the key changes, again, for 2020 is we have updated these figures for the code jurisdictional limits on piping. We constantly have to look back and work with the boiler and pressure vessel code, because as they update the figures, again, you want the figures to be the same in section 1 and in 31.1, because these two codes work very closely together as what can, basically is what I would define a complete boiler, which is the boiler and the piping. The stress equation modifications incorporate B31J stress intensification factors into chapter 2, and appendix G is new. The addition of B31P as an alternative for heat treatment and minimum preheat requirements. Again, this is a consensus document. So what we would hope happens eventually is that all the 31 codes adopt it, and now we have a consensus for heat treatment and minimum preheats, and they're the same regardless, because the materials don't know whether they're going to be used for this service or that service. And then a new content in chapter 6 to allow ND as an additional alternative to hydrostatic testing. We spoke briefly on that. that now it does provide you a path when hydrostatic testing is not practicable. And again, this is not to be used to save money. It's not to be used because somebody doesn't want to hydrostatically test a system. It's extremely onerous. It's very expensive to follow this process. So the rationale to use this has to be real, okay? There has to be a very valid reason why it can't be done, and not just because of cost or I don't want to. Whoa, I think I got one more here. Yeah, I just wanted to, if you'll bear with me, just for those people that that may be on code committees or wish to be on a code committee, some of these items that we try to do take a lot of time, and specifically 121788, which is the alternate NDE in lieu of hydro test. Just to give you an idea of the timeline and what it took to get this through the committee. Pretty much it got opened up in subgroup F&E in 2012, a mere 8 years ago, based on a need by industry. As I stated, that people were saying, hey, there are some applications where we just cannot do this testing. And so they needed an alternate method. So we went, okay, it took a couple of years to get this thing started, but then we grabbed hold of it. And then from 2014 to 2018, it was balloted. In other words, it would go back up to the committee 10 times, and it would, and it would get shot down, and it'd be reballoted and get shot down. And we did this for 4 years, and then finally get the item approved. And the reason for that is any negative comment from the ballots needed to be addressed for an item to go forward. So you can't just leave a comment out there, you have to address it. And ultimately, some of these comments were extremely good, and you would incorporate them into the next ballot. So you're basically trying to, you're polishing this item and taking the rough edges off and making this item better and better and better. So finally, we got it approved by the subgroup, but we weren't done then. And then had to be validated by standards committee, and standards committee people have a very jaded eye as well, and look through the entire item and say, well, we don't like how this is worded, or this is not allowed. And so it's a higher level of review, and that took a few ballots to get through, and another year we finally got that done. And then after we've got both of that done, it goes up to the board. And in July 2019, it was approved by the board and finally made it in time for the 2020 edition of 31.1, which is paragraph 137.8. So if you go to the 2018, it's not there. So just really to see just the stick-to-itness, how long it takes some items. Some items, not so bad. Some items just take a long time because they're a new direction, or there's something that was not previously allowed in the code that we're now trying to allow. And items like that usually take forever because people are very set in their ways, and it's very difficult to change that. But the key takeaway is, and don't forget, that being on a code committee takes persistence and an affirmation from the subgroup to never give up, because the fellow that had this, the project manager, many times he wanted to throw in the towel. He said, I can't do this anymore. I just want to, why don't we just close it? It's a motion to remove it. And the group said, no, it's important that we get this through. So through his perseverance, and I was very pleased that he stayed with it, we were able to finally get it published. So just keep that in mind. On some of these issues take a long time. Other than that, that is pretty much my overview of B31.1. I know it's pretty dry to just go through a code book like that, but hopefully along the way you were able to look at the various sections, because the thing that's important to remember is you can't just take one little portion of this book and go, aha, that's how this is done. You really have to have general knowledge of the entire code, so that when they're speaking of one thing, you understand what the reference is. And that's why there's still, even to this day, so many requests for interpretations, because it's not black and white. There are many gray areas, and sometimes that's by design to give the designer a little bit more latitude. But sometimes as we're looking to fabricate something, we want an answer. And so for the most part, it's easy to work with once you get familiar with the various, tables and equations and things like that. But it is important that you look at the book as a whole and not just as sections. And that's why you got to think of your piping system from inception to operations. And with that, I thank you. And if there are any questions, please let me know.
Oh, thank you. Excellent presentation. I have a couple of questions here. The first one is, what is the reason that B31 does not clarify each item with further explanation, as is done in the 12 sections of the ASME code? Example list of changes in record numbers, and the last word I can read. But did you understand the question?
No, what just maybe simplify it for me. What is the question again?
The question is the reason why B31 does not clarify each item with, I think it does not go in the details as far as I understood from the question. Each item with further explanation as is done in the rest of the ASME code. I don't know if you agree with this assessment, but anyway, this is the question.
Well, like I said, I'm a little confused as to what the inquirer is asking, as far as, so what is this like a list of changes, or what are they looking for? Because we do have a summary of changes in our code.
Yeah, but I think, let me ask you a favor to the person which raised the question to repeat it with granting further details. I will pass to the next one. As edition 2020 is being presented, can we understand that it will be required in edition 2021 of section 1 steam boiler?
Well, right now, the 2020 edition of the power piping is working in tandem, with the 2019 edition of section 1. So when the new section 1 comes out, we then have to review that, and we'll take out new items, which will then be incorporated into the 2022 edition of 31.1. But there's always going to be a slight disconnect because the edition cycles are not the same. But what we do in our committees is once the new code is issued, then we go through there to see if there's anything we need to update. So if section 1, like I said, decides to update the jurisdictional figures again, then we will then take that as an action item for us. And then our figure from the 2020 code may differ from the 2021 section 1 code, but ultimately it'll be corrected in 2022. Okay?
Okay. Thank you, Paul.
Right.
The next one is, as both B31.1 and B31.3 refers to the PCC2 standard that applies post-construction, what is the intention of this reference available?
Well, the intention is to provide further guidance for post-construction activities. We're not endorsing everything there because it may not be applicable. But so what you have to do, and I'm going to use a phrase here, you have to take it with a grain of salt. In other words, you have to, again, use it as it's intended to be used for guidance. But do not infer that our code says that you do everything that it says. So again, it's a normative reference, such as the National Board Inspection Code for repairs. That's a reference. PCC2 is a reference. It's just we're pointing someone in the direction of say, hey, if you want additional information and guidance, you can look here. You don't have to if you don't want to, but you can. So it's just another way to provide additional guidance to the user.
Okay. Thank you.
You're welcome.
And the next one. When does the 2020 edition of B31.1 come into force?
It's usually 6 months after issuance, so it will become mandatory January 1st, 2021.
Okay. The next one. Should the owner define the year in which the project will run? Are there any limits on usage between editions?
Come again with that question?
Okay, let me repeat.
Please.
Should the owner define the year in which the project will run? Are there any limits on usage between editions?
To the best of my knowledge, you can use, you should be, to me, I would, try to use the edition that's current at the time of the contract. But then there's other considerations such as jurisdiction. Jurisdiction may not have adopted the more current edition. So the owner has to, has the ability to pick. But again, once you pick that edition, you use it in its entirety. You don't cherry pick, as I stated. But again, you also have to, besides the owner, you have to look at the jurisdiction where the piping system is going to be installed.
Okay, Chip is watching us, and he asked the microphone. I don't know. Let me ask because he said that if we grant him the microphone, he can help with the previous question.
That would be fine. How do we do that?
You there? Are you there? Are you there?
Yeah, we are hearing you.
Okay. The question had to do with why doesn't 31.1 and 31.3 show the summary of changes much like BPV does? And as the presenter said, that we do provide the summary of changes, but I'm actually not only a 31.3 chair, but I'm also the B31 standards chair, and I sit on the board. So I asked that question too, and what I found out was the boiler code does it that way, and we're looking at doing the 31.1 and 31.3 codes that way. And what that means to us is not only do we put the summary of changes in there, but we're also cross-reference the TN number or the record number like boiler code does. And when we do it that way, when that book editor does it that way, it has a better description. Is the presenter, is that you, Ned? Who's the?
No, this is Paul, Chip.
Paul, that's right, Paul. So that was something that we talked about at B31 Code Week, and found out that basically they outsource the boiler code to a book editor, and they happen to show it two ways, both by, say, paragraph number, and also they change it around and do it by what's called, we refer to them internally, right, as record numbers. So if you look at section 8, the summary of changes are shown both ways, and one is, I think, described a little bit better, but ASME staff does the editing for the B31 books, and we're looking at doing that, cross-referencing it both ways. So hopefully that answered the question.
Well, I certainly appreciate that, Chip. I wasn't aware of the differences between there, but I think hopefully that does answer the question that I wasn't aware of that either, that we're going to look to go that direction. But if it does create a little bit more clarity, I'm all for it.
Yeah, look at boiler code and you'll see how it's cross-referenced both ways, and we only cross-reference it one way. All right.
All right.
Thank you very much.
Thank you.
Paul, the next question is, what is the requirements to certify an inspector for B31.1 and who validates their abilities?
Well, again, like I said, with inspections, you have really a few types of inspectors, okay? For BEP, the inspector is an authorized inspector, and they're going to, verify boiler external piping. All right. So that's a separate subset for piping. Now, as far as non-boiler external piping, the owner is going to designate the inspector. And so in 136.1.4, it does describe what the requirements are for the owner's inspector. So if you read that paragraph there, you've got some criteria that you need to meet. And basically the owner inspector is designated to perform the inspections on behalf of the owner. It shall be an employee of the owner or an engineer or scientific organization or recognized insurance or inspection company acting as the owner's agent. So the idea here is basically you don't want to just select somebody and say, hey, you're my inspector, go out and do this, and he has no experience at all. So what 31.1 tries to do is say, hey, if you're going to call somebody your inspector, make sure they have at least 10 years experience of design, manufacture, erection, fabrication, inspection, and examinations. Maybe you have a professional engineering, registration or some other national recognized equivalent. We also allow, certified welding inspectors or senior certified welding inspectors to do visual inspection on piping. So there's a lot of varieties, a lot of ways that you can become an inspector by meeting this criteria. So remember now, all we're trying to do here in this chapter is to make sure that whoever is selected has the proper experience and education to do the job. So there is some criteria there. You just need to review paragraph 136.1.4.
Perfect, thank you. The
welcome.
next one, we understand reference standards, but are a reference standard a suggestion that we follow or requirement to meet the intent of the standard?
The way I understand it, and if Chip's still online, maybe he can add something to this. The reference standards are usually standards that we're referencing in our code to provide additional guidance. And we're not, mandating that you follow in its entirety this reference standard, but as referenced in our code, then it will provide some additional insight into that topic. So to the best of my knowledge, it's not a mandatory requirement to follow this reference standing, but only to the extent that you glean the information as it is being referenced in our code. I know that's a little weaselly, but I don't really know how best to say that.
Okay, another one here, it's interesting. Please give a brief overview of best practice from a committee view on applying B31.1 to real world experience.
They want me to apply working on the
I
committee.
think it's as far as I understood, it's a case.
I'm not sure I understand where they're going with this question. Do they want to know how sitting on the committee is similar to real world experience?
Yeah, I understand the real world as a case, and it's not. Please give a brief overview of best practice from a committee view on applying. Yeah.
Well, I think that the only thing I'm going to add to this, and I don't know if this is going to really answer this question or not, but the way, when I first joined B31.1, my background is from a company that designs and builds steam generators, of which piping is a subset of that. And because we already had enough people sitting on Section 1, and at that time, Section 9, Section 5, When I asked my boss that I could, can I join the committee? He goes, well, we don't have anybody on 31.1. So I said, okay. So what I did, okay, I brought my experience, and my experience of 40 years was basically from the fabrication side. I cut my teeth working for a fabricator in Pittsburgh for the first 15 years before I went to work for an NDE firm, before I went to work for Foster Wheeler. So what my real world experience is what you see in this code. So that's why, the first thing that I wanted to be a part of was subgroup F&E, fab and exam, because that's where my strength comes from. And the rules and requirements that we set up in this chapter, I wanted to be a part of that process. So, but again, what happens is when you get an item and you go, wow, I really know this topic, and you just go in there and you prepare your item and it gets balloted, and then you get slammed by the designer who knows a totally different side of the issue, or you get slammed by a materials guy, or you get slammed by a utility. So what's nice about the code is it's made up of an eclectic mix of designers and users and fabricators and manufacturers and erectors, so that everybody's point of view from their real world experiences gets baked into this code. And from that, I think, is why, whether it's the boiler and pressure vessel codes or 31.1, that you get the best of the best. The people are volunteering their time, but what you're really getting is subject matter experts in all these various topics, whether it's design, materials, or fab, exam, testing, or O&M. So the way I look at it, the real world plays a very important part in the making up of this code.
Okay, perfect. The next one, it's also interesting. We are very active user of both B31.3 and B31.1. We would be interested in participating in committee work. Do you have an international group like B31.3? And if so, who can we contact to discuss?
I know that they have tried that in the past where they're international working groups, and sometimes it was successful and sometimes not. But I would definitely have them contact our secretary, Umberto Dorzo, to see if they're, if they have an interest, because we're always looking for participants to help us. That yes, we would definitely invite that. But they would have to, ask that information to our secretary, and maybe we can get that set up accordingly.
Another one here, we use section 2 for welding metal filters. When doing the actual welding, what is the maximum allowable misalignment for joining? Are these calculations for a component with the wall extending internally be internally trimmed too?
So you're looking, and you're talking about 31.1?
Yeah, good question.
So if you're just talking 31.1, we have a misalignment requirement of, if you look at figure 127.3-1, if you've got piping components, your butt welding, you can have internal misalignment of 1/16 of an inch, which equates to 1.5 millimeters or less. Now, if it exceeds that, you can correct it by counterboring the thicker member, or the member that's inside, or it's thicker, with a 30-degree max. You can do a counterboring and a taper. So it gives you a methodology, but I mean, without doing any internal preparation, you're allowed 1.5 millimeter or 1/16 of an inch.
Okay, the last one. In 136.2, inspection and qualification of authorized inspector for boiler external piping. Can you
Yes.
explain the stamping requirements? Also, in 136, point 3.2, qualification of NDE personnel. Can you go into the requirements needed for a company and individual?
All right, two-parter, huh? Okay. Again, you know, if you've got boiler external piping, you've got to go back to Boiler and Pressure Vessel Code Section 1, okay? And look for those requirements, you know, for an AI. So I think the definition, I haven't really pulled that up yet, but the definition for the requirements for the authorized inspector is listed in Boiler Pressure Vessel Code Section 1. So because we have the technical authority, but Section 1 has the administrative authority, you have, like I said, you sort of have to use both books. So if you want to find out what the requirements are for the AI, you've got to go back to Section 1. Okay. I don't have that exactly. I don't have it in front of me. I'm just, you know, going through 31.1 at this point. I think the second question was 136.3.2 regarding the qualification of NDE personnel.
Yes.
And 31.1 gives you variety. I mean, you have various ways that you can have a program established. And basically, you know, you want to have this program established by the employer of the personnel being certified. But it needs to be based on these minimum requirements. So A is instructions, fundamentals of NDE method, on-the-job training to familiarize yourself with NDE. So this is like if you were just putting a program together to do 31.1, you need to follow this, A and B. C, you must have a vision acuity examination performed at least once a year and to determine optical capability. And then D, upon completion of your instructions and on-the-job training, the NDE personnel given a written examination and a performance examination by the employer to determine if they're qualified. Okay. And so pretty much A through D gives you a path for qualification of NDE personnel, you know, for a various organization or employer. And then you continue to go on with additional information regarding that if you are certified and you haven't done the specific examination for a period of 1 year, you shall be recertified. And that's typical for welders who haven't welded in a process for 6 months or more to be recertified. So is with the certification of your ND personnel. If there's a guy that's been off for 2 years, you have to recertify him. But again, if you don't want to do that, you have an alternative. So an alternative to that program, you can follow the requirements of Boiler and Pressure Vessel Code Section 5, Article 1, you know, T120E or T120F, to use that as the qualification of your NDE personnel. So now that's your second option. And for visual examination, you have another option that you can use in AWS CWI because they're qualified to QC1, and you can use them as long as they also receive an annual vision acuity examination requirement that's listed in C, and they meet the J1 vision acuity requirements of Section 5, Article 9. So you can see you have multiple methods to certify NDE people. You know, your company just needs to choose what they want to do, but you must follow each section in its entirety. Again, you can't cherry pick and do this one, that one, maybe a little bit of this, a little bit of that. Follow the requirements in their entirety.
Okay, this was the last one, Paul, and I'd like to thank you very, very much for your presentation, and it was very good as well. I'd like to also thanks Chip again for his participation, and if there is no further questions, we are going to finish today, and you talk tomorrow in the second day of our ASME Abendi standards workshop. Thank you very much, everyone.
Well, thank you very much, Antonio, and I thank you for the opportunity to participate in this. And again, I certainly appreciate, it was a learning experience for me to actually to really go through the code from start to finish, because I learned a little bit every time I open that book myself. So the takeaway is just continue to work with the book and continue to expand your horizons with all the sections, not just the particular section you may be looking into.
Thank you, Paul.
Thanks, Antonio.
Bye-bye.
All right, bye-bye. Thanks again.